So basically in this course, we are going to be analyzing, designing, and detailing the foundation for our residential 2-story building. So I already created a course on how to model, analyze, and design this residential 2-story building. So if you've not seen the course, you can check my profile, to get this course. So first of all, you want to get this course so that you can understand how to perfectly model, analyze, and design a reinforced concrete 2-story building from scratch to finish. And this is industry standard. So try to get this course. So as you can see, we've already designed this building. So we are also going to be creating a course on the reinforcement of this building. So for this particular course, we are going to be taking a look at the foundation design. We're going to see what kind of a foundation we are going to be using for our structure, and we're going to be looking at the different type of foundation, and we're going to see how we can analyze and design this foundation. Okay, so this is what we are going to be this is what we are going to be doing in this course. Okay, so now if you want to design your foundation, there are various ways you can design your foundation. You can manually design the foundation. You can get the result from ETABS. You can get the axial load coming on this the axial load on this column that is acting on the point. Then you can take the axial load, then manually design the foundation using using the formulas, depending on your building code. Or you can export the reactions coming on this column joint. You can export them to Microsoft Excel. Then you can design your footing. Or you can also use the software CSI SAFE. So CSI SAFE is also a software by CSI America, and CSI SAFE is mostly used for designing floor system like slabs and foundation. So you can export the reactions. You can export the reactions coming on this column joint. You can export this reaction to CSI SAFE. Export it to CSI SAFE. Then you can design your foundation in CSI SAFE. So we are going to be using CSI SAFE because CSI SAFE is one of this is the industry almost standard for designing foundations. Okay, so we are going to be using CSI SAFE. Or you can also design this foundation right on ETABS. But we are going to be using CSI SAFE because there are more there are more options in CSI SAFE. Okay, so we're going to be using CSI SAFE to design the foundation of our structure. Okay, so this is what we are going to be discussing in this course. So what I would say is try to get the CSI SAFE software. So if you don't have the CSI SAFE software, you can easily request for a trial version. So if you go to the CSI American website, you can request for a trial version. So I think it's a 30 days on trial version. Okay, and I'm pretty sure before it expires, you would have at least learned a lot about foundation design. Okay, so try to get the software. Try to get the software from the CSI American website. Try to get the trial version. Okay, so that you can practice with me. Okay, so this is what we are going to be discussing in this course. So make sure you pay close attention, get all your materials ready, because we are going to be taking a look at foundation and analysis, design, and detailing. Using we are going to be following industry standard. Okay, so this course is going to be really, really different from every other course on the internet, because I'm going to explain to you the reason why are we clicking on certain materials, like why are we doing this, why are we doing that. I'm going to be explaining everything to you in details. Okay, so now the first step you want to take before designing your foundation. So first of all, we are going to be exporting our reactions at the base. We are going to be exporting this reaction to CSI SAFE. So there are different ways. So you can either design your foundation manually, so whereby you take the reaction forces coming at this base. Then you simply calculate, you simply calculate the required area of steel that is needed, for every particular, joint. So you calculate the required area of steel manually, or you can export the reactions to Microsoft Excel. Then you can calculate, the required dimension for the footing, and also the required area of steel, then the required thickness. Or you can export the reactions at this base. You can export this to CSI SAFE. Then CSI SAFE, with CSI SAFE, you can design the foundation. So because as structural engineers, we always want to make our life easy, right? So when I'm going to be using CSI SAFE, I'll be exporting the reactions coming at this base. I will export this to CSI SAFE so that we can carry out, the foundation design. Because CSI SAFE this is the industry standard software we use for designing floor and also for foundations. Okay. So what you need to do is, first of all, I'm going to be exporting the reactions. Now, to export the reactions, you need to go to File. Then you want to go to where it says Export. Then I'm going to be exporting this to CSI SAFE. Okay, so you're going to click on Story as Safe v12.f2k file. Now the story to export. So as you can see, we have this dialog box. So it is saying story to export. So obviously the story to export is going to be the foundation, because we are trying to design the foundation at this foundation level, right? So the story to export is going to be foundation. Now we have a theory load to export option. We have export floor load only, export floor load and load from above, export floor load plus column and wall distortions. Okay, so you need to know, you need to select the right option. So for this, if you select export floor and load only, so what this option does is, this option is only going to export the gravity and lateral and load that is being applied directly to the floor level, that is directly to your selected floor level. You can see the selected floor level here is foundation. So it is only going to export the gravity and lateral load that is directly applied to the foundation, directly applied to the foundation level. Okay. So what it does is, it is going to treat the foundation story. It's going to treat this foundation story as an isolated flat slab. Okay, so it will completely ignore everything happening on the upper floor. So it will ignore this ground floor. It will ignore the first floor, and also it will ignore the roof. Okay, so this is what the export floor load only mean. Okay, so when we would use this, so basically we use this when we are modeling a standard elevated floor slab, or if you are modeling a roof inside CSI SAFE, in order to check its local bending and deflection. Then you can go with this. Export floor load only. Okay, but for our project, you cannot do this, right? Because you cannot select this, because your footing, if you select this option, meaning your footing will have almost zero load, because the weight of your entire structure is going to be ignored, right? So that is why we can select this option. You can only select this option. Let's say you are let's say you are modeling a roof. Okay, you are modeling a roof in CSI SAFE, and you want to check its local bending and deflection. Then you can select this, because it is only going to export the floor load only on the roof. Okay, but for our structure, we can select this. So let's talk about export floor load and load form above. So for the second option, this is the standard industry option. Okay, for designing, for foundation design. So how does this work? So basically, what it does is, it is going to calculate the entire cumulative weight of your structure. As you can see there, it's going to calculate the entire cumulative weight of our two-story building superstructure. That is the weight of the beams, the weight of the column, the weight of the slab, the life load, the staircase, etc. And it is, after calculating this load, then it is going to condense all the multi-story forces into a localized point, right? It's going to condense all this load into a localized point reaction. Okay, so it's going to it is going to condense all this load into this points, right? You can see into this base point. Okay, so we are going to have a localized point reaction like PS, PY, and PZ, and also you're also going to have a moment at this point like MY, MS, and MSZ right at this base joints. Okay, right. Okay, so we are going to use this for standard low-rise, building, mid-rise building, and even commercial buildings. Okay, if you want to design isolated footing, combined footing, or raft footing. Okay, so if you want to also get the load coming from the upper floor, then you need to select this, and we're going to be using this option because we need to get the load coming from the upper floor, which is going to be acting at this base joint. Then if you select this third option, this is basically an advanced settings that is used for complex or massive structural system. Okay, so what it does is it is going to export the column forces. You see the column forces on this story. It's going to export the column forces. Also, it is also going to export the exact physical deformations of this column. That is the axial shortening, the twisting, or the teething. Okay, that this column underwent during the ETABS analysis. So okay, so it is not just going to export. So it is not just going to export the column forces. It is also going to export the physical deformation of this column, right? It's going to, because we know that under massive gravity and load, concrete column, they compress, right? And when they compress, they tend to get shorter, right? That is under massive gravity load. So let's say if an interior column carries a massive load, so let's say this interior column carries a massive load, this column, it might shorten, right? It might shorten less when compared to the exterior column. Okay, so this relative displacement is what we call differential column shortening. Okay, so we tend to use this for super tall buildings and like high-rise structures, like let's say 30 stories and above. Okay, so this is where your cumulative column compression, they add up significantly and they tend to induce secondary bending stresses in the foundation raft. So that is when we can use this. But for normal structure, we tend to go with this. Okay, then we have select load cases. So select load cases. So we are going to be selecting an all load case. So why is this? So we are going to be selecting the load case for just gravity load, because we are going to be using just the service load combination. That is for gravity load. We are going to be using this to check the settlement. To check the settlement, in the foundation, and also I'm also going to be using this to check the soil bearing pressure in our foundation. Then when you want to size your your footing, that is the size of your footing, and when you want to check the punching, the punching shape of your footing, we are going to be using the ultimate load combination, that is the worst case scenario, right? So meaning we are going to also be using this earthquake and wind, the lateral load. Okay, so that is why we need to select all. Okay, you can select all, or you can simply move your cursor like this, select all, click on OK. Then for the load combination, we are also going to be selecting all, because we are going to be needing the service load combination, that is the gravity load, just to check the settlement and also to check the allowable bearing pressure, and also the soil pressure of the foundation. And also we are going to be using the service the ultimate load combination to design the footing, right? So that is why we can also select all, okay, including the envelope, because the envelope is going to give you the worst case scenario. Okay, why P dead plus live, this is going to this is what we are going to be using to check for the settlements. Okay, so we are going to select all like this, then click on OK. Okay, so I hope you understand these three options. So this first option is for if you are modeling a roof. This is if you want to get all the weight of the structure to be acting at this base point. Then this, if you also want to take a look, if you also want to capture the differential and settlement of this column, that is the axial shortening of the column, then you can go with this. Okay, so for now we are going with export floor load and load from above. Then once you're done with that, you simply click on OK. Now you need to save your model. Okay, so I'm going to save this as foundation design course. Okay, so I'll save this on my desktop, click on save. Okay, now we have successfully exported the the reaction at this base to CSI SAFE. Okay, so now what we need to do is we need to open CSI SAFE, then we need to import this the reaction to CSI SAFE. Now, after exporting the load from ETABS, now we are ready to open this. We are ready to import this to CSI SAFE. So we are going to be taking a look at this. So as you can see, this is the CSI SAFE software. This is the user interface. So this is similar to ETABS because both softwares, ETABS and CSI SAFE, both softwares are from the same company, CSI America. Okay, so you are already familiar with this user interface. Okay, now to import the load, right? To import the model from ETABS to CSI SAFE. So what you need to do, you need to come to the file menu. Okay, then you want to go to where it says import. Click on import. Then we are going to go to where it says save F2K test file. Okay, so we're going to click on this save F2K file, and now you need to open wherever you save your model. So you need to open this. So I think this is the model, right? Foundation design. Then you want to click on open. So as you can see, it's going to import. It's going to automatically generate a new model that contains all your column node, the grid line, and also the applied load at the exact coordinates as they were in ETABS. Okay, so you can see this is the user interface. So we have successfully imported the load and the model to CSI SAFE. But as you can see, it seems it looks as if our model is blank, is empty, because we can't see anything at the moment. So because this is foundation design course, right? So we are only designing the foundation. So we only need the foundation to be we only need the the column and node, that is the exact point where we are going to be placing the foundation, right? So this is what we need. Okay, but as you can see, we can't see anything, right? We can't see anything. If you go to let's go to the plan view. If you go to the plan view, click on this. Okay, so if you go to the plan view, like click this, you can see. So we're only having two. We're only having two story, right? The base and story were one. So if you move up in the list, you can see we don't have anything. This is the 3D view. We don't have any point. So what you need to do, the point, the column and node point, they are invisible at the moment. So you need to make this, this point visible. So to make the point visible, you need to click on this icon. Then you want to go another way. It says object present in view. You can see the joint object. You can see the invisible is turned on. So we need to deactivate the invisible so that we can see the column and node points. Okay, so deactivate that. Click on apply. Right, click on OK. So now you can see. So we can see. Let me close this model. Good. So now you can see these are the node. Okay, so this is where we are going to be placing our foundation. Right, we are going to be placing our foundation. So first of all, we are going to try to design this foundation as isolated footing. Okay, so don't worry, I'm going to be explaining the different type of footing in the next lesson. Okay, so you can understand this better. Okay, so you can see now if you right click on this joint. I click on any joint. Now you can see, if you click on the load, you can see the load has successfully been imported, right? You can see. So we have the dead load above, live load, we have the notional load. You can see. So these are the different load cases in ETABS, and this load have been successfully imported. Okay. You can also right click on this. You can see. So this is how you know that you have your model was imported successfully. Okay. You can see these are the load. Okay, and also you can also take a look at let's go to the define menu. Load combination. You can see these are also the load combination. The load combination were also imported, right? You can see these are the different load combinations. Okay. Yeah. So now in the next lesson, we are going to see the different type of foundation. We are going to discuss the different type of foundation. Now, before we proceed to the foundation and design, let's first of all understand the different foundation system. So we're going to be understanding the different foundation system. So in structural engineering, the foundation is the most critical element of a building. So we all know these foundations are very, very critical. They're very important. That is why before designing foundation, we need to make sure, we understand the type of foundation, okay? Because they are critical for our structure. So its sole purpose is to safely transfer the massive weight of the superstructure. Okay, so the purpose is to transfer the weight of the building to the soil, right? So it is transfer the weight of the transfer the weight of the superstructure, such as the dead load, the life load, the wind load, the seismic load, snow load, etc. So into the earth without causing the ground to fail or the building to settle unevenly. Okay, so this is the main purpose of foundation, to transfer the weight of the superstructure into the soil so that the ground, so without causing the ground to fail, right, or the building to settle unevenly. And we have different type of foundation. We have two type of foundation, like we mostly use for structures. So we have shallow foundations and deep foundations. Okay, so let's discuss this type of foundation. So for shallow foundation, these are placed relatively close to the ground surface. So they are typically within 1 to 3 meter deep, right? So they are cost effective and are the default choice when top layers of soil have a strong bearing capacity. So if the soil which your building is going to be sitting on, if the soil has a good bearing capacity, if it has a strong bearing capacity, so you get the bearing capacity from the geotechnical report. Okay, so they're going to do they're going to test the soil with their machines, and they will give you the bearing capacity of the soil. So if the bearing capacity of the soil is good, is strong, then you can go with shallow foundation, and they are cost effective, right? They are cost effective. So that is why in small structures we tend to go with shallow foundations. So we have different type of shallow foundations. So first of all, we have isolated, or we can also call it spread footing. So this is the most common and simple type of foundation, right? It consists of a single square or rectangular concrete pad sitting underneath a single column. So for this isolated footing, this type of footing, like where you are having, like for each column, each column is going to have its own separate foundation. Okay, so there will be a separate foundation. There will be a separate foundation carrying sitting on the column. Okay, so this is all called isolated footing. Okay, so when do we use it? So we tend to use this for standard low to mid-rise building. So okay, so like our two-story residential projects, when the soil is strong and the columns are spaced far enough apart, that the pad don't touch each other. Okay, so if your columns are spaced far, enough, then you can place isolated footing as long as the footing don't touch each other, right? So this is what we call isolated footing. So you can take a look at this. So this is how it will look like. You can see. So for each column, you can see each column has a separate footing. You can see this column has a separate footing. These are the separate footing. So each column has a separate footing. Okay, and you can see they are spaced apart. You can see they are far spaced apart. You can go with isolated footing. Okay, and when the bearing capacity of the soil is strong. Therefore, combined footing. So when two columns are very close together, their individual isolated footings might overlap. Okay, so if two columns are very close together, then they might overlap, right? So in that case, you need to provide combined footing. So for the combined footing, then meaning you are going to place one footing, like just one footing, like for two or more columns. Okay, so they may overlap. A combined footing merges them into one single rectangular or trapezoidal concrete pad. Okay, so something like this will be an example of a combined footing. Like for example, something like this. Okay, we can also say mat footing, but we'll get to that soon. Okay. So where you have one footing for two columns, we call this combined footing. Okay, so when do we use them? We use them when the columns are too close to each other. So when two columns are close to each other, we can't provide individual footing for for each column. So we have to just provide one footing for both columns. Okay, so we can call this combined footing. Okay, so or when a column is located right on the property line, that is when you physically cannot center a square footing without crossing it into your neighbor land. Okay, so if your column is right on the property line, meaning you cannot place isolated footing for that column, because if you place isolated footing for that column, meaning you are going to cross, you are going to cross into your neighbor land, and which is not, which is not acceptable, by by your neighbor. So in that case, you need to provide a combined footing. Okay. Then we also have a strip footing, or we can say continuous footing. So instead of supporting a single column, a strip footing is a long continuous concrete strip that supports the entire length of a load-bearing wall. So if you have a wall, so this strip footing, it will support the weight of the wall. So it is used for load-bearing and structural wall. So this type of footing is used for load-bearing and structural wall. So this is when the length of the strip footing is much higher than the width of the footing. So if the length is much higher, then we can say this is a strip footing. So the length is much higher than the width. So it is provided for a row of column which are so closely or nearly spaced that their individual footing will overlap or nearly touches each other. Thus, in such cases, it is economical to provide a strip footing. So this is an example of a strip footing you can see. So when the length of the footing, you can see the length of the footing is way larger than the width of the footing, and it is supporting this masonry concrete wall. So we can see this is a strip footing. So we use this under masonry wall, concrete retaining wall, or light timber frame residential houses. We can go with this strip footing. Okay. Then finally, for shallow foundation, we have what we call mat or raft foundation. So a mat or raft foundation is one giant, thick, continuous slab of concrete that sits under the entire footprint of your building, supporting all the columns and walls at once. So it floats on the soil like a raft on water. Okay. So when do we use it? So we use this raft foundation when the soil is very weak, right? So if your soil is very weak, the bearing capacity of your soil is weak, you can go with mat foundation. And when the building load are so heavy that isolated footing will cover more than 50% of the ground area. So if your building load, like the load coming from your building like to the soil, is so heavy that the isolated footing will cover more than 50% of your ground area, then if your isolated footing is covering more than 50% of your ground area, then what is the point of providing isolated footing? You will need to go with raft foundation, or when the structure contains a deep basement, right? The mat is going to act as a basement floor. So if your structure contains a very deep basement, you need to provide mat footing. Okay, so it is very excellent for preventing differential settlement. So that is where one side of a building sink faster than the other side. So in order to avoid this differential settlement, you will need to provide raft footing. Okay, so this raft footing is going to be something like this. So where we are going to have one footing like for the entire columns. You can see one footing for the entire columns is going to be a raft footing, or we can say mat footing. So it is spreading like a mat on the soil. Then the second type of foundation we have is deep foundation. So when the top layer of soil are so weak, like soft clay, loose sand, or swampy mud, then in that case, you cannot provide a shallow foundation. You will need to go with a deep foundation. Okay, so this foundation must bypass the weak soil. So it has to pass this weak soil and reach deep underground to find solid rock or dense soil. Then we call this deep foundation. So we have different types of deep foundations. So we have a pipe foundation. So this pipe foundation, these are long, slender cylinders, and these cylinders are made of steel. They might be made of concrete or timber that are driven or drilled deep into the ground. So we said deep foundation is when you deep past the weak soil, you try to find solid rock or dense soil. So meaning this pipe foundation, they will need to, these pipes, they will be driven inside the soil. They will pass through, soft soil in order to find in order to find a deep rock, underground, right? So they are driven or drilled deep into the ground. So they act like underground state for the building. So they carry load in two ways. So this pipe foundation, they carry load, as you can see. So this is how the pipe foundation will look like. So let's say this is your structure, your building, and this is the pipe cap that is that is beneath the the structure. Then these are the pies, you can see. So these pies, they will, you can see they are driven past weak sway. You can see we have lower density, medium density. Then they will need to find hard strata. So this is the hard density. So they will need to be placed on this hard strata. Okay, so these are the pies. So now there are different type of they are different, they carry load in two ways, these pies. So we have end bearing pies. So how does this work? The bottom of the pies, you can see these pies, they rest directly on a layer of solid bedrock deep underground. So this will be an example of end bearing pies. You can see these pies, they are resting directly on solid bedrock. You can see, so on this high density area, you see they're resting directly on solid bedrock. Then we have what we call friction pies, right? So these friction pies, the pie is driven deep, as it is driven into deep swell, and the rough friction between between the side of the pies, right, and the surrounding swell is going to create enough grip, right? It's going to create enough grip or enough friction to hold up the building. Okay, so this is an example of friction pie. You can see. So this is end bearing pie, where the pie is directly driven into the swell to find hard swell. It is sitting on hard swell, but this friction pie, the pie is going to be driven deep into the swell, and the friction, right? You can see the friction between this pie and this swell is going to be so dense, it's going to be so thick that this is what is going to prevent, right? So it is going to hold up the building. Okay, then this is combination of end bearing pies and friction pies. So where the pie is sitting directly on hard soil, and also at the same time the friction between the pie and the soil, is so dense that it holds the building up. Okay. So when do we use this type of pie foundation? So we mostly use this for high-rise structures, right? Like for skyscrapers, okay? And also we use this for buildings that are built on coastal or marshy land, or let's say offshore structures like oil rigs and bridges. Then we also have what we call, so another type of deep foundation. We have drilled shaft, or we can say caissons. So these are essentially massive cast-in-place pies. Okay, a giant hole is drilled deep into the ground. So we dig a giant hole into the ground. Then a massive steel rebar cage is lowered in and it is filled with concrete. Okay, so we drill a massive hole deep into the ground. Then we input, then we place a massive steel rebar cage, and we fill this rebar cage with concrete. So this is mostly used for, for offshore structure. So when do we use it? So we use this structure. They are used for structures with colossal concentrated load, such as massive highway bridge piers or mega tall skyscrapers. Okay, where standard driven pies are not strong enough. Okay, so if your standard driven pies like these pies, they are not strong enough, to hold the structure, then in that case we have to go with this caisson foundation, where you dig a hole deep down, like deep into the ground. Then you are going to place a massive steel rebar cage. Then you fill it up with concrete. You can see, take a look at this image. You can see, so this is going to be, you can see deep beneath, this soil. They are going to place a massive rebar cage inside. Then they will fill it up with concrete, and this is going to create a rigid and dense foundation, which is going to hold up the structure. Okay, so these are the different type of foundation system, for the shallow foundation and also for deep foundation. Okay, so now you understand this. For our structure, we are going to first of all take a look at the shallow foundation. Okay, so we're going to be providing a foundation for each column joint, right? So this is what we call isolated or pad foundation, and we're going to see if this isolated footing can be able to can hold the weight of our structure. So if it doesn't hold up the weight, then we can go with mat foundation. So for a start, we're going to go with shallow foundation, because this is just a 2-story residential structure. Then we are going to check it later if it can pass the check or not. Now that we have verified the imported load, that is the load from ETABS, this load have been successfully imported to CSI SAFE. By just right-clicking on any joint, you can see these are the load. So the load has successfully been imported. Now we need to move to the next stage. So now what we need to do is we need to define the soil subgrade properties. Okay, so this is the next step. So what this basically means is you need to tell CSI SAFE how stiff your soil is, okay, which is underneath your footing. So this is what we are going to be doing. We are going to be defining the subgrade properties. We are going to tell CSI SAFE how stiff the soil, how stiff our soil is underneath our footing. Okay, so to define the subgrade properties for your foundation, so we are going to start with isolated footing. That is, we are going to be having individual footing for every column point, right? So we are going to be starting with isolated footing. Then we can, if any footing is overlapping, then we can design we can design that particular footing as a combined footing. So for a start, we are going with isolated footing because this is just a 2-story residential structure. Okay, so to define the subgrade properties, what you need to do, you need to go to the define menu. Then you want to go to where it says spring property. Then, as you can see, we have a 3 options: point spring, line spring, and area spring. So you want to click on area spring. Now, as you can see, CSI SAFE already there's already a default area spring properties, or we can say soil subgrade properties. So what I'm going to do, I'm just going to modify this. You can add a new property, or you can add a copy of property, or you can delete property, or you can modify this property. So I'm going to modify this. So modify show property. So as you can see, so we have the property name. So you can see this is the subgrade modulus. So it shows compression only, and the unit for this is kilonewton per meter square, which is a kilonewton per meter cube. Okay, so this is the soil subgrade modulus. Okay, so as you can see, the default value, the default value here is 20,000 kilonewton per meter cube. Okay, but we can't go with the default. So how do we calculate this value? So basically, to calculate this value, you need the safe bearing capacity of your soil, which is the SBC of your soil. Then you need to divide this by the allowable settlement. Okay, so you need to divide this by the allowable settlement. So the soil subgrade modulus, the formula for this is the safe bearing capacity of the soil, that is the SBC of the soil, so which you are going to get from the geotechnical report. After doing the after doing the investigation on the soil, the geotechnical engineer, they will give you the safe bearing capacity of the soil. Then you divide that by the allowable settlement of the foundation. The allowable settlement of isolated footing, of isolated footing, you need to check your the building code. So the allowable settlement is 25 millimeter. Okay, so for this soil, the safe bearing capacity, so what this does is it is going to tell you how much weight the soil can actually take before it fails, right, or before the soil shears off. Okay, so this is the SBC of the soil. So the geotechnical engineer, they will do the investigation, and they will give you the safe bearing capacity of your soil, which is going to tell you how much weight the soil can take before it fails. Then the allowable settlement. So the allowable settlement is going to tell you how much the soil will actually compress. And for isolated footing, the allowable settlement is 25 millimeter. Okay, so because we don't have any geotechnical reports, as of now, because this is just we are I'm just creating this course, so we don't have any geotechnical report. So if you are doing this for a university project, right? If you are doing, so what structural engineers do is like they normally assume a conservative value, right? They assume a conservative value. So we tend to assume the SBC of our soil tend to range from 150 kilonewton per meter square to 200 kilonewton per meter square. Okay, so for this course, I'm going to take the SBC of the soil to be 200 kilonewton per meter square. Okay, 200 kilonewton per meter square. So now 200 kilonewton per meter square, you need to divide this by the reliable settlement of isolated footing, which is 25 millimeter. Okay, but you will need to convert the 25 millimeter to meter so that you can get this value in kilonewton per meter. So if you convert 25 millimeter to meter, you're going to get 0.025 meter. Okay, so now it's going to be 200. So when you calculate this, 200 divide 0.0, right? 200 divide 0.025. Okay, so we are going to get the SBC of the soil to be 8,000 kilonewton per square per cubic meter. Okay, so now I'm going to change this value from so I'm going to take this value as 8,000 kilonewton per cubic meter. Okay, so this is 8,000 kilonewton per cubic meter. Now you understand the soil subgrade modulus. So we also have this other option here, the nonlinear option. So we have 4 different options. So we have the for linear, we have the tension only, we have compression only, and we have the elastic plastic nonlinear option. So what are these and what do you need to choose? So you need to understand that you should always go with compression, but let's try to explain all this, like what exactly are these. So the first option we have is non-linear. So when we use this, so basically this is really used for standard shallow foundation, because if you use this, the software is going to assume that the soil can glue itself to the bottom of your footing and pull it down if the footing tries to lift up. If the footing tries to lift up. Okay, so you might use this temporarily for a quick preliminary analysis just to see if uplift forces exist, or let's say for a specific deep pipe foundation where the skin friction provide both upward and downward resistance, then you can use this. But this is really used for standard and shallow foundation. Okay, then we have this second option, which is tension only. Okay, so how does this work? So the spring only engages like when it is being stretched, that is pulled apart. So if you push down on it, it simply collapses and offer absolutely zero resistance. So when we use this, you will almost never use this for for soil. Okay, this is typically used for modeling structural elements like cables, guy wires, or let's say specific tie down anchors, that can hold down things, but they cannot hold things up. Okay, so you really use this for foundation. You mostly use this for modeling structural element like cables. Okay, so that is for tension only. Then this, which is a compression only. So this is the standard settings for soil. Okay, so if you are going to be designing foundation, this is the standard settings for soil. Because why do we use compression only? We know that soil is soil is weak in tension, right? Soil is weak in tension, but soil, they are very good in compression. They can withstand compressive forces. Okay, so this is the standard settings for soil, right? Because soil is great at being compressed, but it has zero tensile strength. Okay, so it cannot grab the bottom of your concrete pad and hold it down. Okay, so this is the exact settings you need for isolated footing. So that is why we go with compression only. Then the final option, which is elasto plastic. So for this elasto plastic, so when we use this, so you use this when you want to model the actual soil failure. Okay, so for example, let's say if you know the ultimate bearing capacity of your soil, that is the SBC of your soil, you can use this value, right? So you can enter the SBC of your soil here, right? You can use it. So let's say if one corner of your footing exceeds that pressure, then the spring is going to yield, which is going to force the software to redistribute the extra stress to the surrounding spring. Okay, so this is when you're going to use this. So if you know the ultimate bearing capacity of your soil, then you can use this value, just to check, like to model the actual soil failure. Okay, then you can input the compression stiffness, the compression strength, the tension stiffness, and also the tension strength. But for standard shallow foundation, you're going to use the compression only. Okay, so this is the default value we're going to be using. Okay, so now we know the subgrade modulus of our soil, which is 8,000 kilonewton per cubic meter. So you can rename this. So I'm just going to call this. Okay, so you can rename this, as to whatever name you want. So I'm just going to call this soil, right? Call this soil, then click on OK. Then click on OK. Right? So now we've successfully defined our soil subgrade modulus. Now, after defining the soil subgrade modulus, now we're going to move to the footing. We're going to define the sizes of the footing and also the area of the footing. Okay, so to define the size, the thickness of the footing, you want to go to where it says define. Then you want to go to where it says session property. So this is going to be under slab session. Click on slab session. So as you can see, we already have ETABS already defined a slab session. So you can either add a new slab property, add a copy, or modify show property. So I'm just going to modify this, modify show. So because this is foundation, right? So when you go to the property data, we are going to select footing, right? So don't select slab because we are not designing the slab, we are designing the foundation. Okay, so we are going to select footing and the slab material. So we are using we are using a C30 concrete, right? We are using a concrete property of a C30. So we are using this. Okay, so so make sure you select the right concrete, the right concrete property. Okay, so we are using a C30. Okay, then a slab. So we can rename this as, let's say, footing. Let's say footing. So the thickness of so we are going to be starting with a trial thickness and size. So if after the analysis and design the thickness is not sufficient, then we can change and we can increase the thickness. Okay, so for now I'm going to go with a thickness of 400 millimeter. Okay, so I'll go with the footing thickness of 400 millimeter. Then the slab property is going to be the concrete property. We are going to be using C30 concrete. Now the modeling type, so you want to make sure we have two options here. So I already explained this in my previous lesson. So but for foundation, if you are designing slab, if you are designing a normal residential slab, you always want to go with shear tin, right? Because shear tin, this is when for shear tin, this is when bending control control the slab, right? Because this is when your slab is very wide, like when compared to the thickness. And in most residential slab, the slab, they are really wide, like when compared to the thickness. Okay, then we go with this shear tin because it is going to ignore out of plane shear deformation. But for shear thick, we mostly use it for foundation, right? Because for shear thick, it is going to include the out of plane shear deformation, right? And we know that for foundation, because isolated footing, they are incredibly thick and rigid, right? They are incredibly thick and rigid when compared to normal residential floor slab, and the size of the footing, I can say this footing, they are not extremely wide when compared to the thickness. So that is why we go with shear thick, right? We go with a shear thick because for this this is going to ensure that the software we accurately calculate the shear stresses on the footing. So we go with shear thick. So always go with shear thick. But for membrane, I already explained membrane. Membrane, this is when the slab is not taking part, in load carrying. Like when you apply load on the slab is going to automatically distribute the load, to its surrounding beam, right? So we don't go with this for footing. We go with shear thick. Okay, so make sure you understand this. So you're always going to go with shear thick for isolated footing. Okay, for isolated footing because the footing size, the footing is not extremely wide when compared to its thickness, and it is going to include out of plane shear deformation. And because isolated footing, they are so rigid, and the column is trying to punch a hole through the concrete. right? It's trying to punch a hole through the concrete. So because of this, there will be extremely, a large and shear stresses, and the software need to calculate these shear stresses. So that is why we go with shear thick. Okay, so I hope this is understood. So for the property type, it is footing. Now the thickness, this is going to be 400 millimeter. Okay, so make sure you input this as 400 millimeter and make sure this is set as footing and not slab. Okay, now for this orthotropic, as you can see, this orthotropic is on check. So you don't want to check this orthotropic, because what orthotropic basically means that your element has different structural stiffness, like in both directions. That is, your element has a different structural stiffness in the X direction than it does in the Y direction. Okay, this is what orthotropic members, this is the meaning of orthotropic member. But for footing, for our isolated footing, you need to leave this boss on check, right? You need to leave this boss on check, because if you leave, because for footing, we know that our concrete has the same stiffness in both directions, right? Our concrete has the same stiffness in both the direction, like it behaves with exact same stiffness in all directions, right? Because a solid concrete footing is what we call isotropic member, right? Because it has the same structure, it has the same exact stiffness in all direction. But if you are designing for, let's say you are designing a rib slab or a waffle slab, right? If you are designing a rib slab or a waffle slab, or let's say a hollow core plank, that is where there is physically less concrete in one direction, then you can click this orthotropic. But for footing, for isolated footing, you need to leave this box on check, because the concrete footing behave like an isotropic member where it has the same stiffness in all directions. So I hope you understand this. So leave this on check. Then for the modifier, for this property modifier, now you might be tempted, to change this property modifier, just like we did for beams, columns, and the slab. But you don't want to change this property modifier for foundation, because you need to understand something. Property stiffness modifier, they are used to simulate concrete cracking, right? They are used to simulate a crack in our concrete. And we know that when a concrete beam or column bend under heavy load, it tends to develop small crack, and this crack tend to reduce the element overall stiffness. But for isolated footing, this is different. Isolated footing, they behave very different, like they behave very differently than your beam, slabs, and column. So why is this so? Because isolated footing, they are extremely thick, like they are thick, compact and block of concrete, and because they are so thick relative to their small span, like for example, the thickness of your footing might be 500 millimeter, while the span of the footing might be 1.5 meter square. So because of this, they experience very little bending deformation, right? So they experience very, very little bending deformation, and because they are so thick, meaning your software, will need to analyze the footing at its full gross cross-sectional stiffness. Okay, so that is why you don't need to change this value, but you don't need to change this value for your isolated footing. Okay, but if you are designing for your beam, column, slab, then you can change the value, because we know that these elements, they crack like under heavy load, and when they crack under heavy load, we need the software to be able to analyze this. But for footing, they are so rigid. For designing footing, they are rigid. They are rigid members, and they experience very little bending. Okay, so that is why we don't need to change this. So I hope you understand this. So click on cancel. So now, after defining the footing property, then you want to click on OK. Then also you want to click on OK. Now the footing property has been defined. Then you also need to know the area of your footing, right? The area of your footing. So you can give a good guess, of your footing area, or you can to get your if you want to calculate your the desired footing area, you can take the service and load, the service actual load from ETABS. Then you divide this by the SBC of your soil. So this will give you the required footing This will give you the required footing area. Okay, so if you go to ETAB, like this is the building, right? If you go to ETAB, if you go to this where it says display support spring reaction, click on this. So you want to use the service load combination, right? For for sizing your footing. So this is very important. So you're going to use just the dead load and the live load. Okay, so let's go with tabulated. So we have FZ. So if your footing is also experiencing, high bending moment, that is a bending moment at this base, then you can select this. But if the bending moment they are so little, then you can ignore this. But let's say, for example, we also select MS and MY. Click on apply. Okay, so let's go to the plan view. Let's go to foundation. Click on OK. So now you can see. So these values are, you can see, so these are the FZ value. Now you can see the MS and MY value, they are so little. You can see they are so little when compared to this FZ value. So we can simply ignore the MS and MY, meaning our footing at this base is experiencing little or no bending and moment. So we can simply ignore this value and we can just focus on FZ value. So for the FZ value, so let's ignore this MS and MY. Click on apply. So for the FZ value, so you want to find your largest FZ. So your largest FZ is something this, you can see, is 442.3 kilonewton. Okay, so now what you're going to do, you are going to take this value, 442.3 kilonewton, you are going to divide this value by the safe bearing capacity of your soil. So we already know the safe bearing capacity of our soil. The safe bearing capacity of our soil was the safe bearing capacity of our soil was 200 kilonewton per meter square, right? 200 kilonewton per meter square. So you're going to divide you're going to divide 442.3 by 200 kilonewton. Okay, so it's going to be 442.3 divide 200. Right, so now we are going to get the required footing size to be 2.21, right? 2.21 meter square. Okay, so now the square root of 2.21 meter square, so it's going to be, so I'm going to have square root of 2.21 meter square. So meaning we are going to get 1.48, right? That is the length of the footing and also the width of the footing. So the length of the footing and the width of the footing is 1.48 meter. So we can round this up to 1.5 meter. So meaning your required footing footing area is going to be 1.5 by 1.5 meter. Okay, so this is going to be your required footing area. Okay, so now we can go back to CSI SAFE. So now all you need to do, you need to draw your footing area. Now, after defining the thickness of the footing and also we know the area of the footing, now we are ready to draw the footing. Okay, so to draw the footing, what you want to do is you want to go to where it says quick draw points around quick draw area around points. Okay, so you want to click on this. Then your shape of object is rectangular, so make sure you choose rectangular, not circular. Then the property, now you need to select your footing. So as you can see, our property is 400 millimeter footing, which we already defined. Right, the local axis, keep this as 0. Then the X dimension, now this is where you need to input your footing size. So we are going with 1500 millimeter, right? So we have 1500 millimeter by 1500 millimeter, or we can say 1.5 meter by 1.5 meter. Okay, so now all you need to do, you just need to click click the points, and your footing will be drawn around this point. Okay, so first of all, I'm going to start with this. You click, as you can see, now we have successfully draw the first footing. Then you simply do the same for every other column and point, because this is where we're going to be having our footing. So I'll place my footing here, place my footing here. We have one footing at this point, we have a footing at this point, we have a footing at this point, this point, this. So we have a footing at this point. So make sure none of your footing are overlapping. Okay, it's very important. Make sure none of your footing are overlapping, or the footing, they are not too close to each other, right? It's very important. Okay, so draw a footing here, draw a footing here, draw another footing at this point, draw another footing at this point, draw another footing at this point, draw a footing at this point, and finally we draw a footing at this point. Okay, beautiful. So now once you're done, you simply click on select objects. Okay, now you can see these are the footing. So we have drawn the footing, but now we need to assign the soil property to this footing, because if you click on this footing, right click on this, you can see there is no our soil subgrade modulus has not been assigned to the footing. You can see no, they have not been assigned to the footing, because we need to assign this to the footing. Okay, so now to assign this to the footing, so what we need to do, we need to select all footing, right? So to select all footing, you need to go to the select menu, go to select, go to properties, then go to slab section. So we are selecting this footing 400 millimeter. Click on select, click on close. Okay, so now we need to assign the soil subgrade modulus, so that we can tell CSI SAFE that this footing is having this soil property. Okay, so that is why it is very important we assign the soil subgrade modulus to the footing. Okay, so now to assign this, you need to go to the assign menu, then go to the assign menu, then go to where it says let's see, go to share, right? Then go to slab session. Sorry, not this. Close soil subgrade. Go to assign, then go to let's see, shell. Yeah, area spring. Yeah, you need to find where it says area spring. Click on area spring. So this is the soil, right? So you need to assign the soil to the footing. So select the soil, then click on apply. Beautiful. Click on OK. Now you can see the soil subgrade modulus has been assigned to each footing. Now, after drawing the footing area, and also after assigning the soil subgrade modulus to the footing, let's quickly take a look at the different load combination. So like I said earlier, we are going to be using two types of load combination. We are going to be using service load combination and ultimate load combination. So the service load combination, this is going to be used to check the allowable settlement of the footing, and also it is going to be used to check the soil bearing and pressure. Okay, then for the ultimate load, then for the strength combination, we are going to be using this to check the punching shear of the footing, right? That is the two-way shear and also the one-way shear. Then also we are also going to be using this, to determine the size, the reinforcement area that will be needed for our footing. Okay, so let's go to the define menu. So you can see load combination. So you see we already imported this different load combination from ETABS, to CSI SAFE. So this P dead left load. So this is going to be the service load combination. So this is what we are going to use to use to check the settlement and also the soil pressure and check. Therefore the ultimate, which is the strength, we are going to define an envelope for for each of these individual combination. Okay. So this is what we are going to do. So click on add new combo. So I'm just going to call this envelope. I'll say, because envelope is going to give you the worst case scenario, right? So I'll say envelope ultimate, or let's say envelope strength. Envelope strength. Okay. So the combination type, you're going to select envelope, right? So now you need to click on this drop down. So we are going to add the different load combination, right? So starting from this. So you add this. So the scale factor should be 1, right? Click on add. Then the next load combination is going to be this, right? This. You click on add. Then we're also going to add this other combination. This combination. You click on this. Then add. Then we're also going to add this other combination. Okay. So this is very important. You need to do this. Click on add. Because when ETABS didn't import the envelope from ETABS to CSI SAFE. Therefore, this, as you can see, we're having from case 1 to 12. So you are selecting just one. Select this one. Click on add. Okay. Then, okay, for this, you select this one, right? This minus case. Click on add. Okay. So this one we're having from 1 to 12. Then this, you also select this, my plus 1 WY. Click on add. All right. Which is plus 1 WY. Let's see, plus 1 WY minus 1 W is 1 WY. Okay, so then the next is going to be this minus 1 WY. Click on add. Okay, so you want to do this for a different load combination, right? Okay, this one. Okay, minus 1 WY 12, then plus this, so 0.5 WS. Click on add. We have minus 0.5 WS. Click on add. Then plus 0.5 WY. Add. Then minus 0.5 WY. Okay, click on add. Then we have this plus 1 WS. Add. Then minus 1 WS. Click on add. Then we have plus 1 WY. Click on add. Then minus 1 WY. Right, click on add. Okay, then we have plus 1 QS, right? You can see plus 1 QS. Click on add. Then what else do we have? Then we have minus 1 QS. Click on add. Plus 1 QI. Click on add. Then we have minus 1 QY. Click on add. Then we also have plus 1.0 NY. Click on add. So this NY, these are the notional load. We already discussed this. And then finally, we have this. Okay, yeah, finally we have this. I think that is the last one, right? Yeah, this is the last one. Okay, so this is going to fall under the envelope. So we're going to be using this. We're going to be using this to check for the punching chair, and also we're going to be using this to to design the reinforcement. Okay, so I'm going to say envelope strength, then click on OK. So make sure the combination type is set to be envelope, not linear. So click on OK. So now we are going to be using these two combination, the envelope strength and also the P dead life, right? If you click on this modifier, you can see, so this is comprising of just the dead load, and this is comprising of just the dead load and also the dead load and also the life load, right? You can see the dead load and the live load. Click on OK, then click on OK. Now, after understanding the service load combination and also the strength load combination, which is needed for our footing, now before we proceed, we need to take a look at the mesh option, right? We'll need to understand if we are going to mesh our foundation slab or not. So the answer to that question is yes. We are going to be meshing our foundation slab because when you selected share tick for your footing property, like when you went to define menu, the soil property, the slab section, if you modify this, you can see this was share tick. Okay, So when you selected share tick for your footing property, what you did is you told the software to analyze the concrete pad, right? The concrete pad using the finite element method, that is FEM. Okay, but here's the thing: FEM, which is finite element method, cannot analyze a large blank geometric shape all at once, right? How does it work? It works by dividing that large shape, right? You can see this large footing slab shape. So it works by dividing this large shape into a network, right? Into a network, or we can say into a mesh of hundreds of small intercoordinated elements, and these are usually square or rectangular elements. Okay, so why is this meshing required? So you know that your soil property is defined as area spring, right? So if we don't mesh, without meshing, the software is only going to calculate the soil reactions at every four corners of your footing, right? So it's going to calculate your soil reaction at this corner, this corner, this corner, this other corner. Okay, so it's going to calculate. It's going to calculate the soil reaction at every four corners of your footing, and the meshing create hundred of internal node points, right? It creates hundred of internal node points, which will allow the software to assign a small portion of the soil spring stiffness into each micro node, okay, which is going to give you a smooth and highly accurate contour map for your soil property. So that is why we need to mesh our slab, right? Because it is going to give us a more realistic result. And it's going to give us a more realistic and smooth, a contour map of our soil pressure. Okay, of our soil pressure. And also, meshing is the only way the software can actually can accurately determine the exact location where the bending moment, is at peak, and where the punching shear capacity tend to drop. So that is why we need to define the. We need to define the mesh. Okay. So luckily for us, ETAB, there's, you don't need to manually draw this mesh. You don't need to manually draw this mesh on your slab. CSI SAFE, CSI SAFE, we can handle this, automatically, right? So CSI SAFE handle this dynamically behind the scene through what we call automatic slab mesh options. Okay, so what you just need to do, you just need to define the mesh, and the size of the mesh. Then CSI SAFE will automatically do this behind the scene, and it will automatically mesh your slab, right? That is your footing slab. So that is why we will need to mesh we will need to mesh this slab. So to do that, what you need to do is you need to select all your footing area, right? You need to select all your footing area. So we are going to select properties, slab section. So this is the footing, right? Click on select. So you can see all footings have been selected. So now let's go to the assign menu. Then you want to go to shell, right? Click on shell. Then you want to find where it says, you can see floor auto mesh option. Right, this is what you want to check. You want to click this floor auto mesh option. So click on this floor auto mesh option, right? Or let's just a minute, go to analyze. Yeah, analyze. Okay, let's check this one. There's automatic mesh settings for floor. So you can also use this automatic mesh settings for floor. Okay, so for this, so we are using the rectangular mesh. So use localized meshing and mesh joint where possible. So you need to select this. So now this is where we need to input the size of the mesh. Okay, so the size of our mesh is going to be 0.5 meters, because why are we inputting 0.5 meter? For normal standard residential isolated footing, which range from, that is the footing area range from 1.2 meter to 1.8 meter in footprint and width. So a 0.5 mesh size is a structural engineering sweet spot. Okay, because what this does is, it break a 1.5 meter footing into a clean 3x3 grade of sub elements. Okay, which is going to provide a superb analysis precision. Okay, so that is why we are going to be going with 0.5 meter. Okay, so we are going to be going with 0.5 meter. Then you click on OK. right? You click on OK. Now we can actually see the mesh. We can actually see this mesh if it is working or not. So what we can do, we can go to click on this set display option. So under the general option, you can see under other special elements, you can find where it says share analysis mesh. Click on this share analysis mesh, click on apply. Now you can see these are the mesh. You can see, so it is dividing our floor into 3 by 3. You can see, so three at this part, 3 at this part, 3 at this part, 3 at this part. Okay, so this is going to give us a more accurate results, and this is why we are using a 0.5 meter mesh. Now, after meshing the footing slab, we are ready to run the analysis. Okay, so you can go to analyze, quickly check your model, check model. So 2.5 millimeter or 1 millimeter. Click select all, click OK. So we don't have any warning, so that is fine. Now go to the analyze. Let's see, set load cases to run. Okay, so we are running all load case, right? We're running all load case. Go to analyze. So once you're done with that, you simply click on run. You simply click on run analysis. Then you save your model. Yes. Then you're gonna wait for the model to be analyzed. Beautiful. So now you can see our foundation has been analyzed. So this is according to the dead load. You can see this is the displacement as per the dead load. Okay. So now the first thing you want to check for your foundation, there are different check you want to check for your foundation. So the first check you want to check is the soil bearing pressure check. Okay. So you want to check this against and seeking. So why are we checking the soil bearing pressure check? So you need to make sure that your footing area, that is the length and the width of your footing, is large enough in order to distribute the building weight without overloading the soil. Okay, so that is why we are going to be checking this soil bearing pressure to make sure that the footing area, that is the length and the width of the footing, is large enough to distribute the building weight without overloading the soil. Okay, so we are going to be checking this. We are going to be checking this against the soil bearing capacity. So if the soil bearing pressure, we are getting due to the service load combo, if this is higher than the soil bearing capacity of the soil, meaning our foundation is going to fail under the soil, our foundation is going to fail under the soil bearing pressure check. Okay, so you need to make sure your soil bearing pressure check is you need to make sure your bearing pressure you are getting from the service load combination is lesser than the SBC, that is the safe bearing capacity of your soil. If this is lesser, meaning it passed the soil bearing pressure check, and your foundation is not going to sink, right? Your foundation will be large enough to distribute the building weight without overloading the soil. Okay, so let's check this. So now what you need to do is you need to you need to find where it says display soil pressure. Okay, so click on display soil pressure. So now we are going to be using the service load combination. So I said this earlier, we are going to be using the service load combination to check for the soil bearing pressure, and also we are also going to be using this to check for the allowable settlement of our foundation. So you want to click on combo, then you want to find where it says P dead life, right? So this is the service load combo. Okay, then you want to click on apply. Okay, you want to click on apply. So now you want to make sure that these values are lesser than the safe bearing capacity of our soil. If the value you are getting from the soil pressure, if they are higher than the safe bearing capacity of the soil, meaning your footing is not safe against sinking, meaning your footing area is not large enough to distribute the entire weight without overloading the soil. Okay, So in that case, you have to increase your footing area so that it is large enough to to distribute the weight, okay, without overloading the soil. So now let's take a look at this. You can see, when looking at this, you can see the maximum value we are getting is over 225, right? 225 kilonewton per meter square. And you can see this, if you take this particular footing, we're having the soil bearing pressure of this particular footing to be lesser than 200 kilonewton per meter square. So this particular footing is passing the soil bearing pressure check. You can see this. But if you take a look at this particular footing, at the middle, you can see this particular footing. You see the soil bearing pressure at this part. You see this is 210 kilonewton per square meter. So meaning this is exceeding the safe bearing capacity of our soil. Also take a look at this particular footing. This footing is also exceeding the safe bearing capacity of our soil. You can see this is 212 kilonewton per square meter. Then this footing, okay, this footing is fine. This footing is also fine. This footing is fine. These footings, they are all okay. So you can see the exterior footing. You can see this footing at the exterior perimeter. These footings, they are okay. You can see they are way lesser than 200 kilonewton per meter square, which is the SBC of the soil. So what we need to do is we are going to try to increase the area of this particular footing. You can see it makes sense because this footing, this footing, we're having a column at the middle of the building, and this column is resting on this footing. So because the column at the middle of the footing is taking is experiencing maximum load when compared to these other columns. So obviously the column at this particular footing is going to be carrying larger load, and this larger load is going to be resting on this particular footing, and also it is also going to be resting on this particular footing. So that is why this particular footing is failing the safe bearing capacity check. Okay, so what we need to do, we need to increase the area of this footing so that there's enough area for the footing to distribute this pressure to the soil. Okay, so we are going to change the area of this footing and also the area of this footing. But for these footings, they are okay, right? You can see they are lesser than 200 kilonewton per meter square. Okay, so what I'm going to do, I'm going to unlock the model. So just these two footing, right? So I'm going to select this, then I'll also select this footing. So now I need to go to define session session property. Let's go to slab session. So I'm going to add a copy of, no, sorry, not this. I need to go to draw quick area around points. Okay, so for this, so initially our footing size was 1,500 by 1,500 millimeter, right? So now let's increase this to 1,600 by 1,600 millimeter. Okay, so let's increase the area of this. So, but before that, let's delete this particular footing. Let's delete this. Select this, delete. So we are going to redraw the footing again. So click on this. So this is going to be 1,600 by 1,600. Click on this point, and also click on this point, right? Okay. So make sure you assign the subgrade modulus. So select both footing, click on assign, go to shell, area spring. So you assign this soil, click on apply. Okay, then you also need to mesh this. It's very important. So go to analyze, and this. So this is 0.5. Then okay, yeah. So we are good to go. Now let's rerun the analysis. Yes. Now you need to save your model. Okay, so let's check the soil bearing pressure. So click on this display soil pressure. Make sure the combo is P dead life. Click on, make sure this is on the form shape. Click on apply. Okay, so now let's take a look at this. So we're having the maximum sweat pressure. This is 190. Let's take a look at this maximum sweat pressure. So yeah, we're having 194. Yeah, we're having 185. Yeah, this is 150. Yeah. So finally, we our footing has passed the sway bearing. Our footing has passed the sway pressure check. So these values, you can see the maximum value we're having here is 190. So this value, they are lesser than 200 kilonewton per meter square, which is the safe bearing capacity of our sway. So we can say our footing is safe. Our footing area, the footing area we provided for each footing is large enough, right? The footing area we provided for each footing is large enough to be able to distribute the weight to the sway. Okay. Then if you take a look at this particular footing, you can see, we also need to be able to design our footing economically, right? This footing, take a look at this. This is 93, and this is way lesser than 200 kilonewton per meter square, right? Which is the same capacity of the sway. So it will be economical for us to reduce the footing area, because if we go with this, meaning we are just wasting, we are going to be wasting, we are going to be wasting concrete, right? Because more area, meaning we are going to be, demanding for more concrete, right? And this is also very expensive. So why can't we just reduce this? Also, take a look at this. This is also way lesser than 200 kilonewton per meter square. So we can reduce this in order to make our footing more economical. Okay. So what we can do, we can reduce this outer perimeter footing, right? We can reduce the area so as to make our footing to be more economical. Okay, so I hope this makes sense. So what I'm going to do, I'm going to reduce this. What about this? Okay. So what I'm going to do, close this. Let's unlock the model. Unlock the model. So I'm going to select this footing, this. Okay, sorry. Select this footing. Select this. Okay, now we can reduce the area so as to make our footing to be more economical. Okay, deselect this. I don't need this. Okay, and let's go. Yeah. Having something like this is fine. So now what I can do, I can delete this. Then I'm going to redraw the footing again. So click on draw quick points around the area. So instead of 1,500, let's go with 1,200. Or let's go to 1,000. Yeah, let's try 1,200. 1,200 millimeter. So like you simply click on this point, click on this point, this, okay? Just so that we can make our footing to be more economical, right? You understand this? To make our footing more economical. So after selecting this, so now just all we need to do is we need to select. Okay, what we can do, just go to select properties, slab session, footing 400, click on select. Now let's assign the sway bearing. So go to assign shell load, sorry, not shell, shell, then area spring, assign the sway property, click on OK. Okay, so select this property, slab session, so footing, you can select. So you can quickly mesh this. So go to assign, sorry, analyze. So okay, so now let's rerun the analysis. We can save, yes. Okay, because this perimeter footing, the columns, they are carrying less load, so that is why these values are lesser. So to make our foundation design economical, we need to reduce the footing, right? We need to reduce the size. Okay, so I hope this makes sense. Okay, so let's click on the soil pressure check. Click on apply. Click on OK. So now you can see this. Look at the values we're getting. So 130, 143, see 195, see 98. Yeah. So now finally we can go with this value. We can go with 1200 by 1200 millimeter. Okay, can go with this value. You see, they are still passing the check. They are still passing the soil bearing pressure check. So we can go with this value. So we have made our foundation design to be more economical. Now, after taking a look at the soil pressure check, now we know that our footing is passing the soil pressure check. So what we're going to do next is we're going to take a look at the settlement check. So we're going to check if our footing is safe against sinking and teething, right? So we need to make for isolated foundation, or we can say shallow foundation. The arrival settlement for shallow foundation is 25 millimeter, right? That is, the settlement should not exceed 25 millimeter. If it exceeds 25 millimeter, meaning your footing is not safe against sinking and teething, right? So meaning your footing is actually sinking, due to the load coming from the super structure. And we don't want such a scenario, because if this happens, meaning it is going to lead to structural cracks in your wall above, right? So we don't want this to happen. So that is why we need to check for this. We need to check for the arrival settlement. And if your footing is settling less, then it is fine. But if it is setting like more than 25 millimeter, then you probably need to increase the footing area, so that the foundation, like, it has enough area to distribute on the load. Okay, it has enough area to distribute the load on the soil. So let's check this. So I will quickly rerun the analysis. So click on save. Yes. Okay, so now let's go to display. Let's go to the true deform shape. So now we are going to be using the service load combo, right? I said this earlier, which is dead load and life load. So service combo, dead load plus life load. And then you click on apply. So now you want to check if any particular footing is settling less, is settling below 25, is settling above 25 millimeter. So you can see, if you take a look at this is 12 millimeter, this is 13 millimeter, these are all fine. What about this? This is 19. So at this point, you can see this is 24.558 millimeter. This is 22 millimeter. This is 11. These ones are fine. So as you can see, the maximum value we're having for the settlement of this footing, this is 24 millimeter, which is located at this particular footing, right? This particular footing. So this is the maximum value. This is 24.558. It is negative because this is it's a downward it is a downward force, right? So that is why it is negative. So this negative 24.558. You can see at this part, this is negative 22.556, right, millimeter, right? Okay, so it is negative because it is compressing down, like on downward. Okay, so I think this the settlement for our footing is below 25 millimeter, which is fine, right? It is below 25 millimeter, so we can go with this. Okay, so I think it passed the settlement and check. But if any particular footing is settling above 25 millimeter, then this will mean that the downward force from your column is compressing your swell spring way too much. Okay, way too much, and meaning you will need to increase the footing area, right? You will need to increase the footing area, right? Because we said that the pressure, pressure of settlement, is directly proportional to the load over the area. Okay, so by increasing the area of your footing, meaning you decrease the stress, that is being applied to your sway spring, which will directly reduce the settlement. Okay, so that is how you can increase. That is how you can solve the settlement check. So if it is exceeding 25 millimeter, you simply increase the area of your footing. Okay, so but for our footing, you can see they are way. For our footing, you can see they are way below 20. They are below 25 millimeter. And also, this is what you need to also understand. While checking your 25 millimeter limit, you also need to check. You also need to check the difference in settlement between the neighboring footing, right? So let's say, for example, if column A, or we can say if column if footing A, if let's say if this particular footing settles 24 millimeter, and the neighboring footing, which is this other footing, this footing settles, let's say 5 millimeter. Now, there's going to be a difference of 19 millimeter, right? So there's a difference of 19 millimeter settlement. So this differential settlement will wrap your ground beam and cause structural crack in your superstructure. So while checking for the allowable settlement, just to make sure that it is not exceeding 25 millimeter, you also need to make sure that the difference in settlement between two neighboring footing, this difference in settlement, they are not, at least they are reasonable. So if this footing settle 24 millimeter, then the neighboring footing should at least settle, let's say 20 millimeter, or let's say 15 millimeter, or let's say 20 something millimeter. But if this other footing is setting like, let's say 3 millimeter, you can see there's a huge difference. And because of this huge difference, there's going to be differential settlement, and which because of this differential settlement, it is going to lead to crack in your superstructure members. Right, so this is what you also need to understand. So if you take a look at this, for this particular footing, this is 24 millimeter, right? This is minus 24.5 millimeter. This footing is certainly minus 24.5 millimeter. While this other footing, you can see this footing is certainly minus 23 millimeter. You can see minus 23 millimeter. So there is not a huge difference. So meaning there is no differential settlement, for this particular footing. Now take a look at this other footing. This footing is settling, let's say this is 13.45 millimeter, right? What about this? This is settling 12 millimeter. So you can see there is not a huge difference between, there's not a huge difference between the settlement or the settlement of this footing, right? So just take a look at, 2 or 3 neighboring footing, and you need to make sure that, the difference in settlement is not, that huge, right? So if you take a look at this particular footing, this is 18.9, this is 18.89, while this is 20. So this is fine. What about this? This is 20 millimeter. So this is fine. So we don't have any differential huge differential settlement for our footing. So we can say this is fine. But if you have any huge differential settlement, then meaning you need to try to increase the area of, let's say this footing is certainly 20 millimeter, while this other footing, that is the neighboring footing, is certainly just, let's say 2 millimeter. Right? Let's say this other footing is certainly just 2 millimeter. Then you need to change the area of this footing so that the settlement kind of match the settlement of this other footing in order to avoid differential settlement. So I hope that makes sense. So now as you can see, our foundation has passed the settlement check, meaning we are good to go. Now, I just want to quickly say some things about the differential settlement and check. So we know one of the most common cause of differential settlement in our design of footing is that these footings, like they are sized uniformly without considering the massive difference in the column and load. So for example, let's say your heavily loaded column, like let's say your heavily loaded column at this particular footing, let's say this is experiencing more load, let's say 445 kilonewton, than your outer perimeter column. This perimeter column, let's say they are experiencing less load, let's say 150 kilonewton, 150 kilonewton. So obviously, your heavily loaded column at the middle of your grid, this column, they will naturally gauge deeper, like into the swell, than your lightly loaded column. And if they are giving similar size, then you might experience differential settlement. Okay, so to fix this, to fix it. So what you can do, let's take a look at this particular footing. So let's say this footing is having settlement of 2 millimeter, while this footing is having a settlement of 20 millimeters. So you can see there's a huge difference. So what you can do, there are different, ways, like there are various ways you can sort out this differential settlement. So what you can do, you can unlock your model, then you will keep your small column footing. Like let's say this footing is a small column footing, and let's say the area you provided for this footing is 1.2 by 1.2 by 1.2 meter. Then you also provide the same area for this footing, 1.2 by 1.2 meter. So what you can do, you can increase the size of this footing, of this heavily loaded column. You can increase this size to, let's say, 1.6 by 1.6, so that this footing is going to settle less, which is going to kind of match with the settlement of this other footing. So which will prevent that differential settlement. Okay, so that is one way. Or the second way, what you can do is you can introduce a ground type beam, right? Or what we call strap footing. Okay, so if you have a couple of columns, that refuse to stabilize, they keep failing the differential settlement check. So you can structurally tie them together, right? So let's say this footing and this footing, after increasing the area of this heavily loaded column, the settlement, is still way higher compared to this settlement of this other footing, which will cause differential settlement. So what you can do, the second way, is you can introduce a tie beam. So you can introduce a tie beam that will tie this footing to this other footing. Okay, which is going to make them to settle as a single unit, right? So if you introduce a tie beam that tie this footing to this footing, then they are going to settle as a single unit, which will eliminate the differential settlement. Okay, so you are basically going to introduce a stiff, heavily reinforced concrete strap beam, or we can say tie beam, right? That is going to directly connect the isolated footing at the isolated footing pad at the foundation level. Okay, so the bending rigidity of the concrete beam physically restrain the weaker footing from sinking independently, which is going to which is transferring a portion of its excess load over to the neighboring more stable footing. Okay, so this is the second way we can reduce the differential settlement. Now the third way, way you can reduce the differential settlement is you can basically introduce a combined footing. So if this footing is settling way less compared to this other footing, then what you can do, you can, instead of providing isolated footing, because we know that when columns are spaced closely together, right, these two columns, for this footing, because they are spaced closely together, then their individual pressure bulbs, right, in the soil is going to overlap. Right, the pressure bulb of this footing and the pressure bulb of this other footing, they are going to overlap, right? They are going to overlap, so when they overlap, they compound the settlement behavior. So in order to prevent this, because they are overlapping and they will cause differential settlement. In order to prevent this differential settlement, so why not just provide a combined footing? So provide a combined footing for this particular column and also for this particular column. Okay, so instead of keeping them as a single isolated part, then you can simply merge them into a single continuous combined footing. Okay, so this is going to prevent the differential settlement for this footing. Okay, so or what you can do, if after you find out that even after providing the combined footing, you are still having the differential settlement. So what you can do, you can improve the ground, right? You can improve the ground, like you can change your subgrade, right? You can change your soil subgrade modulus, right? So that is where you have to contact your geotechnical engineer. So you go back to your soil property definition, so let's say initially, if your soil, if you go to the define menu, session property, slab session, slab session, no spring property, area spring. Right, so modify. So you can see your value. The value was 8,000 kilonewton per cubic meter. So what you can do, you can contact your geotechnical engineer. You can contact your geotechnical engineer to improve the soil subgrade modulus. Right. So if you change the soil subgrade modulus from, let's say, 8,000 kilonewton per cubic meter you improve this to a much stiffer value, let's say 20,000 kilonewton per cubic meter, then automatically your soil is going to be stronger, right? And it is going to be able to resist or withstand the pressure that is coming from the column, right? So meaning in that case, your footing is going to settle less, right? It's going to settle less, which is going to reduce the differential settlement, right? It's going to reduce the differential settlement for the neighboring columns. Okay, so these are the different ways you can pass the differential settlement check. But for our footing, you can see we don't have differential settlement check. You can see for these neighboring footings, they are, as you can see, they are not much. You see, this is the settlement for this is 19, for this is 23. So the difference is not much. So we don't have differential settlement. But if you have any differential settlement, so these are the various ways you can pass the differential settlement check. Now that we know our foundation is passing the settlement check, the differential settlement check, the soil pressure check, now we need to move to the punching shear check. That is the safety against column piercing, right? So this is what we call the punching shear check, or we can say this is the two-way shear check, right? So it is either the punching shear or the two-way shear. Okay, so this check is very important. So this is a critical concrete failure mode where the heavy column load is trying to punch a clean square hole straight down through your footing pad. So that is why we say this is also called two-way shear, because it is trying to punch a clean square hole, right, straight through down your footing pad. Okay, so this check is going to tell you if your footing is actually thick enough to be able to resist this punching that is coming from the column. Okay, so if your footing is not thick enough, let's say you have a footing thickness of 200 millimeter, meaning the column is going to try to punch through the footing, through the footing. Okay, so we don't want such a scenario to occur, because if your column punches through the footing, meaning it is going to lead to failure. Right, it's going to lead to failure. So in that case, you have to increase the thickness of your footing so that it pass the punching shear check. Okay, so we don't want a scenario where our column is punching through the footing. Okay, so that is the meaning of the punching shear check. Okay, so now to check for the punching shear, now you need to make sure that the punching shear ratio is less than 1, right? So if your ratio, let's say you're having a ratio of like 0.65, meaning your footing thickness is completely safe and it passed the check, right? But if you're having a value greater than 1, that is a ratio greater than 1, meaning your footing is overstressed, right? Meaning the footing is too thin and it will fail by shearing. Okay, so in that case, you have to increase the thickness of your footing. Okay, so let's take a look at this. So what you want to do is you want to go to display. You go to display. Now, this is the beauty of CSI SAFE. CSI SAFE is going to automatically give you the punching shear ratio. Okay, so you don't have to manually calculate this. CSI SAFE is going to give you the capacity. It's going to give you the capacity ratio of for the punching shear. Okay, so this is the beauty of using the CSI SAFE software. Okay, so for that you can see we have show punching shear design. So click on this show punching shear design. So now you need to make sure that none of these values are greater than 1, right? So let's take a look at this. So this is 0.12. This one's fine. This is 0.1, 0.1, 0.1, is 0.3, 0.3. Yeah. So now you can see these values, they are okay, right? You can see these values are okay. You see, we don't have any value greater than 1. You can see. As a matter of fact, you can see these values, they are way lesser than 1. So meaning this shows that the footing thickness we provided was for this footing, they are okay. But like I said earlier, we also need to design economical. We also need to design economical foundation, right? Take a look at this value. This value is 0.19, 0.12. This is way lesser than 0. Is way lesser than 1, right? So meaning we can't just go with this value because it is going to make our footing to be way less economical, right? So meaning our footing can also, let's say, if we provided a footing thickness of like 400 millimeter, meaning the footing we can reduce this thickness, right? So let's say 300 millimeter, but you need to go with the minimum of 250 millimeter because you cannot reduce your, your thickness to the extent that, the thickness of your footing is so thin, right? Because you will need at least some considerable amount of thickness. But we can reduce this to 300 millimeter. And let's check if it is also passing the punching shear check. If it is passing the punching shear check, meaning we have just saved ourselves, we have just designed an economical footing, meaning we've just saved ourselves money because more thickness mean more concrete, right? And more concrete mean more money, right? So that is why we are going to try to reduce this. So you see, for this perimeter column, for this perimeter footing, we can reduce the thickness, right? We can reduce the thickness. But for this, we can leave this as it is. Let's reduce the thickness for the perimeter footing, or let's just reduce the thickness for all footing to be 300 millimeter, right? Because you can see this value is also 0.3 ratio, not millimeter. This is ratio. So meaning we can also reduce it because this is way lesser than 1. This is way lesser than 1, right? So we can also reduce this. So let's unlock the model. Okay, unlock the model. Now let's go to define section property, right? Slab section. So this is 400 millimeter. Let's go to modify. So now let's reduce the thickness to 300 millimeter. Okay, 300 millimeter thickness. Then the footing, let's say this is 300 millimeter. But we are not going below 300 millimeter. 300 millimeter is going to be the minimum because we don't want our footing thickness to be too thin, right? So the minimum is going to be 300 millimeter. Then click on OK. Then click on OK. Now let's rerun the analysis. Click on save. Yes. Okay, so now let's go back to display, then show punching shear design. Okay. Yeah, so you can see we're still getting the same value. Now the punching shear ratio for this as you increase, you can see 0.5, 0.5, and which is also way below 1, So we can reduce this further because it is going to make our our foundation thickness to be too thin, and we don't want such a scenario. So we are going, although these values are still 0.1, but we are going with this. So this is going to be the minimum we are going to be using. Okay, so this is 0.1, 0.3, 0.55, 0.3. So you can see they are passing the punching shear check. Okay, so this is demand versus the capacity ratio. So this is what we want for our footing. We don't want the column to punch through the footing, and for our foundation, this is not the case. It passed the punching shear check. Now that our footing is passing the punching shear check, or we can say the two-way shear check, so what we're going to do, we are going to move to the one-way shear check. Okay, so this is what we are going to do. We are going to be taking a look at the one-way shear check for our footing. And this is very important. While punching shear, which is also known as two-way shear, usually govern the thickness of an isolated footing. They usually govern the design. If your footing pass the two-way shear check, then it will automatically almost pass the one-way shear check. But this one-way shear check, which is also called the beam and shear, can occasionally govern the design, right? That is, especially if your footing is very long and rectangular, then this one-way shear check, it can govern the design instead of two-way shear check. So that is why we just want to check for this one-way shear to see if it is also passing the check. Okay. Now, unlike the punching shear, CSI SAFE does not have a magic one-click button to check for the one-way shear for an isolated footing. But for punching shear, CSI SAFE will automatically give us the value. But for this one-way shear, CSI SAFE is not going to automatically give us the value. We have to manually calculate this value ourselves, and we have to manually check them ourselves. Okay, so that is what we are going to be doing. But before that, I'm just going to quickly explain the concept of a one-way shear check. Okay, so let's say, for example, let's say, for example, this is our footing. This is our isolated footing, for example. Okay, let's say this is isolated footing. Then we have a column, right? We have this column. Okay, yeah, we have this column. Now, for two-way shear, that is the punching shear, like the critical section for two-way shear is usually at a distance of d, like at the distance of d over 2 away from the face of the column. That is the perimeter of the column. So it's going to be something like this distance, because the column is trying to punch through the footing. So this part, at the distance of d over 2, we are going to have the critical section, right? Which is around this, as in this perimeter like this. They are going to be the critical section. So this is for the two-way shear, that is the punching shear. Now for the one-way shear, Control Z. Okay, so for the one-way shear, what will be the critical section? One-way shear, the critical section is going to be at a distance of d, away from the face of the column. So d is the effective thickness of your footing. So at the distance of d, so either in this face, let's say at this face, this distance, at the distance of d, this distance, right? So this whole area is going to be the critical section for our one-way shear. So if you are taking a look at this distance in the s direction, then this will be the critical section. Then if you are taking a look at this, this part, like in the y direction, so at the distance of d, which is the effective depth of the footing, this distance, like this whole area, right? This whole area is going to be the critical section, right? This whole area is going to be the critical section. So your footing is going to try to shear along this, along this face, okay, or it's going to try to shear also along this face. That is why we say one-way shear. So it is shearing just in one, in one face. But for the two-way shear, which is a punching shear, it is shearing around the perimeter of the column at a distance of d over 2. So what is d? D is the effective depth, right? So d is the effective depth of your, of your footing, right? So let's say the thickness of your footing. Let's say, for example, the thickness of your footing is 500 millimeter. So you're going to take 500 millimeter, right? Then you need to subtract the cover, right? The concrete cover of your footing, and the concrete cover is usually 75 millimeter. So you're going to subtract 75 millimeter. Then also you have to subtract. Let's say you are using a bar diameter of let's say 16 diameter bar for your footing. Then you have to subtract half of the diameter of the bar, right? So it's going to be -8. Okay, so whatever value you get, this is going to be your effective depth, right? So this is going to be your effective depth, right? So at the distance of this effective depth, this is where you are going to get your critical section for the one-way shear. So this whole area is going to be the critical section. So this whole area is going to try to shear off, right? When due to the load that is coming from this column. So this whole area is going to try to shear off, and we say this is one-way shear. Or this whole area is also going to try to shear off. We say this is one-way shear. Or this area at this part is going to try to shear off, or this other area is also going to try to shear off. So that's why we say that is why we say it is one-way shear. Okay, so if you go to the ACI code, so you can say for shallow foundation in section 13.2.6.2, for shallow foundation members continuously supported by soil and design based on the assumption of rigid behavior of the shallow member. So if you want to find your one-way shear, your one-way shear strength, that is VC. So VC, this is basically the capacity of the concrete to resist shear. Okay, so VC, this is the formula, and this is in metric unit, right? Because this is the code ACI 318. M stands for metric. So if you want to calculate VC, you are going to use this formula, which is 0.17. Then multiply by lambda. Lambda is a unit weight factor, which is for normal weight concrete. Lambda is always taken as 1.0. Then FC prime is the compressive strength of your concrete. Then BW is going to be the width, right? The width along the critical the critical section. While G is going to be the effective depth, right? This is going to be the effective depth of your footing. So once you calculate for VC, you multiply this by, you multiply this by phi, right? So the phi for concrete is, the phi for shear is 0.75. Okay, now after getting this, so your goal, you need to ensure that the ultimate shear force that is pushing up on this, that is pushing up on this chunk of concrete, this critical area, VU, we call this VU. So VU, how can you get VU? VU, you get this from the from your ETABS software, right? You get this from your ETABS software. So VU is the demand, right? VU is the demand. So you need to make sure that VU is less than the shear strength of the concrete itself. So the shear strength of the concrete is VVC, right? This is VVC. Okay, so you already know VC, right? VC, you use this formula to calculate VC, right? Then you need to multiply this by the strength reduction factor of phi. So the strength reduction factor for shear is 0.75. So after getting VVC, then you compare VU with VVC. So you need to make sure that VU is always equal to or lesser than VVC. Okay, so if VU is lesser than or equal to VVC, then meaning your footing is passing the one-way shear check. But if VU is greater than VVC, then meaning your footing is going to fail in one-way shear check. Okay, so this is what we need to do. Now you need to understand this. You see this value B sub W. So this is the width, but we are calculating this width per meter, right? We are calculating this width per meter, because if you go to CSI SAFE, now if you go to the display menu, then let's say we go to show force, then shear stresses. Now for the resultant forces, we are going to be taking a look at V13, which will be the S direction. Then also we are going to take a look at V23, which will be the shear and the stresses in the Y direction. So if you click on V13, click on apply. Now you can see this value is in kilonewton per meter. You can see, so we are getting the stress per meter width. Okay, so that is why this B sub W is also going to be the width of this is going to be per meter, right? Which is 1 meter. We can say 1,000 millimeter. Okay, so this is what you need to calculate. Then you have to compare your VU, like that is the value you are getting from CSI SAFE. You have to compare this to VVC, to check if your footing is passing the one-way shear check or it is failing the one-way shear check. Okay, so let's quickly calculate the value of VVC. Okay, so let's calculate the value of VVC. So VVC, right? VVC, this is going to be equal to, okay, so let's calculate the value of VVC. So VVC, we know this is going to be 0.17, right? So this is going to be 0.17, right? 0.1.17, right? Or multiply by phi. First of all, okay, let's first of all calculate VC. Then we are going to, whatever value we get for VC, we are going to multiply this by phi, which is 0.785. Okay, so just a minute, let me write the formula. So let's write the formula so that it can be, yeah. So let's write the formula. So for VVC, so this is going to be phi, right? Phi, which is 0.75, then multiplied by, so this is going to be multiplied by 0.17 lambda, right? 0.17 lambda. So lambda is a 1 for normal weight concrete. Then multiply this. You have to multiply this by phi, square root of VVC, square root of FC prime, which is the compressive strength of your concrete, right? Square root of FC prime. Then now you have to multiply this by, so we know that this is BW, right? BW multiplied by G. Okay, so BW, so we are taking a look at the shear strength per meter width, right? So we have to multiply this per meter, because we want to get the value in millimeter, so we have to convert meter to millimeter, which is going to give us 1,000 millimeter. So multiply by 1,000. Okay, then you have to multiply this You have to multiply this by G. Okay, you have to multiply this by G. Then now you need to divide all this by 1000 because we want to get the value in kilonewton, right? Because the for FC prime, the square root of FC prime, we are getting this value in Newton, right? Because this is megapascal. We know that megapascal, this is Newton per millimeter square, right? Megapascal is Newton per millimeter square. Okay, so we need to convert this Newton to kilonewton. So that's why we need to divide this by 1000. Okay, we have to divide this by 1000 so that we can get the value in kilonewton. Okay, so it is going to be in kilonewton per meter. Okay, so it's going to be in kilonewton per meter. So now we just have to calculate this value. So we know phi is 0.75, right? Phi is 0.75. Right, then multiply this by 0.17, then multiply by 1, right, which is lambda. The value for lambda is 1. Then you have to multiply this by the FC prime, which is the compressive strength of our concrete, and the compressive strength of our concrete was 30 megapascal, right? 30 megapascal, which is going to give us the square root of 30, right? Square root of 30. Then you have to multiply this by 1000. Multiply this by 1000 per meter width. Then now you have to multiply this by G, which is the effective depth, right? You have to multiply this by G, which is going to give us the effective depth of our footing. So we know. So for that, I'm going to look at the critical section for punchy chair. Let's go to display, show punchy chair design. So this is the critical section, right? For this part, right? This is the critical section. So what I'm going to do, we know that the thickness of this footing is 300 millimeter, right? So because the thickness of this footing is 300 millimeter, so let me say to calculate the G is going to be 300, then minus the cover for footing, which is 75, then minus. So let's say we are going with a bar diameter of 16 diameter bar, right? So which is 16 mm. The half of that is going to be 8, right? So now we need to, this is going to be 300 minus 75, then minus 8, which is going to give us, so G, the value for G is going to give us 217 millimeter, right? 217 millimeter. This is going to be the value for G. Okay, so this is going to be multiplied by 217. Okay, this one multiplied by 217. So all you need to do, you just need to calculate this value. Okay, then you need to make sure you divide all these. You divide all these by 1000, so that we can get the value in kilonewton. Right? You divide all this value by 1000. Okay, so this value is going to be 0.75. So it's going to be 0.75. Then multiply by 0.17. Then multiply by the square root of 30. Right, multiply by the square root of 30, then we have to multiply by this value 217. Okay, multiply by 217. Okay, we get this value, then we divide by this 1000, right? Divide by 1000, so I get this 0.15. Then we have to multiply by this 1000 because it is per meter width, right? So now we have to multiply by 1000. So we are going to get a value of so that is the value for phi VC now. So this value is going to be phi VC. Okay, so phi VC is going to be equal to 151.54, right? 151.54 kilonewton per meter width. Okay, so this is the shear capacity of our concrete. This is the shear capacity of our concrete. So now we know this value, we can simply go to CSI SAFE. We can check the value of VU, which is the demand, right? Which is the shear demand. We can now compare this value to our phi VSC. Okay, so now let's go to CSI SAFE. So what you need to do, you need to go to the display menu, go to where it says show forces stress diagram, click on shear stresses forces. Now you need to go to the resultant forces. So we are going to be taking a look at V13 and V23. So VF1, this will be the stress in the S direction, that is if you are going along the S direction, while V23, this will be the stress in the Y direction, that is if you are going along the Y direction. Okay, so let's click on V13, then click on apply. Okay, so now we need to take a look at this stress. I think this was the maximum punching shear, right? So let's take a look at this particular footing. So we know that the value for VVC is 151.54. So we need to get the value for VU to be lesser than this value so that it can pass the shear, it can pass the one-way shear stress, right? Okay. So let's see if it is lesser than let's see if it is lesser than 151. Okay, so we know we said at a distance of a G away from the face of the column, but we didn't draw the column. So right, so let's just what we are going to do, let's just move our cursor, at this point, and see if any value is lesser than 151 kilonewton, right, per meter. Yeah, but normally, if you do the column, then all you have to do, you just need to from the face of the column, you measure the distance and D, which is a 151. Sorry, which is I think it was 127 millimeter, right? So it was 217 millimeter, right? So you measure this distance from the face of the column, but we didn't do the column. So let's just since this is the S direction, right? So let's move our cursor across this, across this zone and see if any value is lesser than 151. If any value is greater than 151 millimeter. So you can see in the S direction moving like this, you can see we don't have any value greater than 151 millimeter, right? You can see we don't have any value greater than 151 millimeter. Yeah, good. You can see, so in the S direction, we don't have any value that is greater than 151 millimeter. Also in the other direction, you can see we don't have any value that is greater than 151 millimeter. Okay, yeah, you can see we don't have any value that is greater than 151 millimeter. So this is for the S direction, right? So meaning this is passing the one-way shear check in this in the S direction, right? Because the value for VU, which is the demand, it is lesser than the capacity, right? Because VVC is 151 kilonewton per meter. And as you can see, we don't have any value greater than 151 kilonewton, right, per meter. Okay, so in both directions, right, in this positive S direction and the negative S direction, as you can see, we don't have any value that is greater than 151 kilonewton per meter. So meaning this is passing the one-way shear check. Okay, so we know that if our foundation is passing the two-way shear check, that is the punching shear check, it will almost automatically pass the one-way shear check. Okay. So you can see, take a look at this value. So this value, so for this, okay. So this one is fine, right? These values are fine, right? So we can go with that. Therefore, F23, which is the stress in the Y direction, click on apply. Okay. Now for the stress in the Y direction, let's take a look at this. You can see in the Y direction, we don't have any value greater than 151 kilonewton. Also in this other direction, we don't have any value greater than 151 kilonewton. Okay, same with this value. You can see like this is the Y direction, so you have to move upward, right, in the Y direction. So you can see, take a look at this. We don't have any value that is greater than 151 kilonewton, right? We don't have any value greater than 151 kilonewton. So same goes for this value. We don't have any value greater than 151 kilonewton. Okay, so you can manually check this for for the footing. You can see we don't have any value greater than 151 kilonewton. So meaning this is passing the one-way shear. This is passing the one-way shear check, right? You can see we don't have any value greater than 151 kilonewton. Okay, you see we don't have any value greater than 151 kilonewton. So we can theoretically say that our footing is passing the two-way shear check, which is the punching shear check, and also it is also passing the one-way shear check. Okay, so if your footing is, let's say for example, if your footing is failing the punching shear and maybe probably also failing the also failing the one-way shear check, then what you need to do is you need to increase the thickness of your footing, right? Because if it is failing the punching shear, meaning your footing is not thick enough, right? Meaning the column is trying to punch through the foundation, it's trying to punch through the footing, meaning your footing is not thick enough, so you have to kind of increase the thickness of your footing. Or let's say if you can't increase the thickness of your footing, then you have to provide what we call pedestals. Okay, you provide pedestals so that the footing is going to be the column is going to be resting on the pedestal, then the pedestal to the footing. Okay, so the pedestal is going to try to prevent the pushing effect from the column to the footing. Okay, so you can either increase the thickness of the footing, and if after increasing the thickness of your footing and the column is still punching through the footing, then you will need to introduce what we call pedestals. Okay, so this is how you can tackle the punching shear and also the one-way shear check. Now we are going to move to the design of the isolated footing. So there are two methods we use for designing the isolated footing. So we can either go with the strip-based method, or we can go with the finite element-based method. Okay, so let's try to understand this method. So for the strip-based method, so what this basically does is this is going to force the finite element software to behave like a traditional structural engineer doing the hand calculation. Okay, so what it does is it look at your footing as a series of imaginary concrete beam. Okay, so how does this work behind the scene? So what you do is you draw a physical part, what we call a design strip, directly over a row of columns. Okay, so for this we are going to have a design strip that will consist of a column strip, and this column strip is going to be the highest stress zone, right? That is directly under the column, and we're also going to be having a middle strip, which is going to be the lower stress zone. That is the lower stress zone between the column. Okay, so when you run the design, CSI SAFE is going to ignore your individual mesh and node. So instead, it is going to capture all the tiny scattered bending moments inside that strip lane, right? Inside that strip lane, and it is going to integrate across the width of the strip. Okay, so so the output of this, the output is going to give you a combined bending moment, MU, for that specific lane, which is going to be measured in kilonewton meter. Okay, it's going to be measured in kilonewton meter. So for this, CSI SAFE is going to tell you the total physical steel area that is needed for for that specific strip width. Okay, so let's say for example, you're having a strip width of let's say 1.5 meter wide strip, and this 1.5 meter wide strip it requires 1,200 millimeter square of total steel at the bottom. Okay, so what you do is you do a simple division. Okay, so let's say if you want to use 16 diameter bars, which will have an area of 201 millimeter square per bar, so the number of bar you're going to be using is 1,200 millimeter square divided by 201, which is going to give us 5.97, which you can round to 6 number of bars. Okay, so this is for the strip based method. So you are going to be drawing a strip, and this strip we are going to be having the column strip and the middle strip, and the reinforcement area that is required is going to be along that strip. Okay, so this is for the strip based method. Then for the finite based method, we can also call this the point by point approach. So the finite element method, or FEM, this base design, like it is going to completely throw out the concept of beams and lane, right? Like in the strip based method. Okay, so what it does is it designs the footing based on the pure physics of a flexing shear element. Okay, so it is going to evaluate the exact stress at every single localized point in your mesh grid. Okay, so for this, you don't have to draw any strip. You don't have to draw any strip. So SAFE is going to look directly at your 0.5 meter grid, 0.5 meter mesh grid line. We said we mesh the footing area to be 0.5 meter, right? So SAFE is going to look at directly at this 0.5 meter grid and line. Okay, so what it does is does, because this is calculated point by point, right? This finite element is calculated point by point. The forces the forces are going to be calculated per unit width, right? Per unit width, and the resulting steel demand, steel demand is going to be, we are going to get the steel demand as millimeter square per meter, like that is like per meter width. We are going to get the required steel demand. Okay, so so this is for the finite element method. So for this, you don't need to do any setup. You just click your design, and automatically CSI SAFE is going to give you the required area of steel, and it is going to catch the peak stress concentration perfectly. Okay, and this is the default this is the default design by CSI SAFE. So I'm going to be explaining, as in both of this method, we are going to see how we can actually design our our footing using the strip-based method, and also using the finite element-based method. But because we are designing isolated footing, and if your column align in a reasonably straight line, like if your column they are done in a really in a straight line, like in a straight grid, then you can go with this strip-based method, because this will give you a very clean traditional output that is easy to drop into a standard foundation and schedule table. But if your column or your footing, they are heavily staggered or offset from each other, as you can see, these footings, they are not 100% at a perfect grid, right? You can see they are scattered, and they are not aligned. They are not aligned perfectly. So in that case, drawing a strip will become a geometric nightmare. So in that case, you want to go with the finite element-based method, because this is going to look at the peak color value of each footing, and it's going to use that number to pick a uniform bar spacing across the entire pad. Okay, so we are going to discuss this. We are going to discuss first of all, we are going to discuss the strip-based method. We are going to see how we can use the strip-based methods to get the required area of steel, and also we are going to look at the finite element-based method to see how we can get the required area of steel. But at the end of the day, we are going to be going with the finite element-based method. Now we understand the strip-based method and the finite element-based method for designing the reinforcements in our footing. Let's first of all take a look at the strip-based method. Let's see how we can use the strip-based method to design the footing. Okay, so CSI SAFE is going to organize your design strip into two directional layers so that they don't interfere with each other. That is for the strip-based method. So we're going to be having the layer A, which is used for the S direction. That is from left to right in the S direction. Then we're also going to be having layer B, which is used for the Y direction. That is from up to down in the Y direction. Now let's see how this works. So what you want to do, you want to go to the draw menu, click on the draw menu. Then you want to find where it says draw design strip, or you can use the shortcut. So the shortcut, go to the left side of your screen, the left menu. You want to find where it says draw design strip. So click on this draw design strip. So as you can see, we have the type of object is a strip. Now we have the strip layer. So we're having two layers, right? So layer A is in S direction. Layer A is the S direction, while layer B is the Y direction. Okay. So first of all, let's start with the S direction, which is layer A. Then we're having strip design type. We're having the column strip, and we're having the middle strip. So for designing, you'll be going with the column strip, because the column strip, this is the strip that is close to the column, right? The strip close to the column, and because the strip close to the column, this area is where we experience high stresses, right? At this area, we're experiencing high stresses. So because of these high stresses, meaning the reinforcement demand is going to be high, right? And because we are designing for worst case scenario, you want to go with the part that has a high the highest shear stresses. Okay, because the column is trying to punch through the footing, so the area around the column, like the area close to the column, is going to be experiencing high stresses, right? So due to these high stresses, then it is going to give us the reinforcement area that will be needed to counteract these high stresses, right? So that is for the column strip. Now for the middle strip is the part that is far away from the column strip. So let's say this region, like this region. So this part is far away from the from the column, is far away from the column. So because this part is far away from the column, this side is going to be having, this part is going to be having very little stresses. And because it is having very little stresses, then the reinforcement demand is going to be low. So because of that, we tend to, for this footing design, we tend to ignore the middle strip. We design this for the column strip, because the column strip is where this is the region that is having the high stresses, and we are designing for the worst case scenario. So that is why we go with the column strip. So I hope you understand this. So we are going to be using just the column strip, not the middle strip. Okay, so now we're having a start width left, start width right, end width left, end width right. So and we're having this value here 1000. So what do we need to input? What do we need to input as the start width left, start width right, end width left, and on the end width right? So let's say your footing dimension. Let's say your footing dimension is let's say 1.2 meter by 1.2 meter. That is for square footing. So for that, if your footing dimension is 1.2 meter by 1.2 meter, so the width of your design strip, this width of your design strip, need to match the exact physical width of your footing, right? You need to match the exact physical width of your footing. So if you're having a footing width of 1.2 meter, then the design strip, you need to divide that by you need to divide 1.2 meter by 2, which is going to give us 0.6 meter, right? So meaning the strip should extend 0.6 meter to the left of the column, right? And also 0.6 meter to the right of the column. Okay, so in total, so to the left of the column is 0.6, while to the right of the column is also 0.6. So in total, we are getting 1.2 meter. Okay, so meaning it is going to cover the full, it is going to cover the entire width of your footing. Okay, so this is how you design for this. How you design for this. So you need to take the width of your footing, you divide this by 2, then that will be your strip and width. So you start from the left to the midpoint of the column. Then from the midpoint of the column, you go to the right. So because we're having a square footing, right? So it is going to be the same. Like it is going to be the same in the x direction and also in the y direction. But if you're having a different, let's say you're having a rectangular footing where the length is different from the width, then so you first of all, let's say in the x direction, this is 1.2 meter, while in the y direction, this is 1.5 meter. So for this for the x direction, like for column, the strip layer A, so because your strip is going like this in the x direction, meaning you need to use this width, like the y width, right? So you have to divide that 1.5 by 2, right? You have to divide that 1.5 by 2, which is going to give us 0.75. So this value is going to be 0.75. Then when you move to the strip layer A, the strip layer B, which is going to be the strip, along the y direction, meaning you are going to be using this S dimension, right? So you are going to be using 1.2 by 1.2 divided by 2, which is going to give us 0.6. So you have to input 0.6 here. Okay. So I hope that is understood. So now let's take a look at the dimension of our footing. So go to draw dimension line. So let's see. We know we're having a square footing, not a rectangular footing. So from this point to this point, you can see this is 1.2 meter. Okay. So meaning, so 1.2 meter divided by 2, this is going to give us 0.6, which is 600 millimeter, right? Because these values are in millimeter. So meaning this design strip width is going to be 600 millimeter. Now because we are having different thickness, right? So we're having different size of footing, right? So we can't use the same 600 millimeter for every footing, because we're having different sizes, right? So, but if you take a look at this perimeter footing, they are of the same size, right? This perimeter footing, they are of the same size. So first of all, we are going to use the same strip width for every perimeter footing. Then we are also going to calculate, we are going to see the dimension of this footing, and we are going to use a different strip width. So how that is understood. So now for strip layer A, which is in the x direction, so all you need to do, so first of all, you need to turn on your snap option, the midpoint, so that you can highlight the midpoint. So go to the draw menu, go to snap option. So make sure line end and midpoint is highlighted. Click on apply, okay. So now we have the midpoint. So from this point to this point, which is zero, sorry, it's a mistake. Let's escape this, Control Z. We have to first of all input the strip, okay. So for this strip, so this is going to be 600, right? Because this is 1,200 millimeter divided by 2 is going to give us 600, right? So this is 600 right? Then also this is also 600. Then this is also 600. Okay, so now we can, so from this midpoint to this point, as you can see now, we have the design, we can see the width of this strip. Okay, then from this point to this other point, then hit enter. So we can see the width of this strip. But if you don't want to see the width of this strip, you can click on this set display option. Then go to other assignment, turn off show width, click on apply. Okay, so we can no longer see the width of the strip. Okay, so this is for strip layer A. Right now, to draw the other strip in the other direction, you need to change from strip layer A to strip layer B. Okay, and we are using the same column strip and the same width, right? Because this is a square footing. So you simply move from this point to this point, then from this point to this point. Okay, then hit enter. So we are done with this particular footing. So you do the same for this other footing, right? Because they are same. Okay, so you start with strip layer A, which is in the S direction. Okay, from this point to this point, then from this point to this other point. Okay, so this strip we need to cover the entire width of the footing. So that is for strip layer A. So make sure you change this from A to B in the Y direction, right? So now from this other direction, it's going to be from this midpoint to this point, then from this midpoint to this other point, then hit enter. Okay, so now we are done with this. Then you move to this other footing as well. So make sure you change this from strip layer B to strip layer A in the S direction. So from this point to this point, from this point to this other point. Okay, so we're going to be getting the reinforcement on this strip. So that is why we are drawing the strip. Okay, so for the layer B, you need to change to layer B. So this is going to be from this midpoint to this midpoint, then to this point. Okay, then hit enter. Okay, so now I'm going to pause this video. I don't want the video to be too long, so I'll quickly draw the strip for this other perimeter footing. Okay, so also you do the same. You draw this strip for this other perimeter footing. Then I'll be back. So now you can see we have successfully drawn the strip for the perimeter footing. You can see. So if you want to show the strip width, so you need to click on this set display option. Then you want to go to other assignments. Then click on show width. Click on apply. So as you can see, these are the strip width, which is covering the entire width of the footing. As you can see, these are covering the entire width of the footing. Okay, so now let's move to the other footing. So for this particular footing, so let's see, go to the draw dimension line. Let's take a look at the width of this footing. So this is 1.5 meter, and this is the same with this other footing. But I think for this other footing, I think the dimension is different. Draw dimension line. Let's see. For this, okay, this is 1.6 meter, right? Draw dimension line. I think this is also 1.6 meter. Escape. Draw dimension line. Yeah, this is also 1.6 meter. Okay, so these footings, they are 1.5 meter by 1.5 meter, but this two footing is 1.6 meter. Okay, so let's take a look. Let's draw the strip for this 1.5 meter footing. Okay, so you want to go to draw design and strip. Click on draw design strip. Then now, first of all, let's start with the strip layer A. Okay, so because this is 1.5 meter by 1.5 meter, so we need to divide by 2, which is going to give us 0.75, which is 750 millimeter. So now the new strip width is going to be 750 millimeter because this needs to cover the entire width of the footing, right? So this is also going to be 750 millimeter. Then this is also 750 millimeter. Okay, so now we have the strip width, so we can simply start placing the strip. So make sure the strip layer is strip layer A, which is in the S direction. So you want to make sure you start from the midpoint to the point of this column, then from this column to this other points. Okay, so this is the first strip. Then hit enter. So now we need to change the strip from strip layer A to strip layer B. Okay, from strip layer A to strip layer B, and this is also column strip. So now we place from this midpoint to this point, then from this point to this other point. Okay, then hit enter. Okay, so I don't want to see this strip width for now, so I can turn off the strip width. so that it doesn't get confusing. Click turn off the show width. Okay. So likewise, you do the same for every other. Likewise, you do the same for every other footing with 1.5 meter width. So I'm going to pause this video. I'll quickly draw the strip width, then I'll be back. So you can see we've successfully draw the strip for this other footing. So if you want to take a look at the strip width, you can simply just go to set display option, other assignment, turn off the show width, then click on apply. So that you can see we have the strip width. Now we are left with this other footing. So for this, we know the width of this is 1.6. So we just have to change the width to from 1.5 to 1.6, right? So click on show design strip. So because this is 1.6, so 1.6 divided by 2 is going to give us 0.8, which is going to give us 800 millimeter. Okay, so you simply just have to change this from 750 to 800. Okay, just have to change this from 750 to 800. This is also going to be 800, while this is also 800. Okay. Okay, so you simply click on draw design strip. So for this, the S direction, right? For this in the S direction, this A. So this is going to be from this point to this point to this point. Hit enter. Then from this midpoint to this point, sorry, escape. Yeah, it has to be draw design strip. Okay, so now we have to change the direction from A to B, right? So now this is going to be from this point to this point, then from this point to this point. Okay, then hit enter. Okay, so now you can see we have successfully draw this the design strip for this other footing. Okay, so you can see, so this is how to draw the design strip for your footing. Okay, so this is how to draw your design strip. So for strip layer A and also for strip layer B. So we're going to be using this, to check our reinforcement, the required area of ST that is needed. Now, after drawing the design strip, we are ready to run the analysis. Okay, so before you run the analysis, first of all, you want to make some check. You want to input some necessary parameters that will be needed for the design. So what you want to do, you want to go to the design menu, click on design menu, then you want to go to where it says concrete slab / beam, click on view revised preferences. So for this, so these values, they are fine, right? These are the fee values, right, for tension control, compression control, and shear. So these values are okay. But for this minimum cover for slab, so the clear cover, this should be 75 millimeter, like for footing. While the clear cover for the bottom, this also should be 75 millimeter. Okay, so this is for to prevent corrosion, right? This is to prevent corrosion on the rebar. So this is 75 millimeter at the top and also 75 millimeter at the bottom. Okay, so this is really important. And also the preferred bar size. So this preferred bar size, so what bar size are you going to, what bar size are you going to be using for your reinforcement? So this bar size is required so that ETABS, so that CSI SAFE can correctly, calculate the effective depth, right? The effective depth, DE. Okay, so use this to calculate the effective depth, DE. So let's say our preferred bar size for footing, let's say we are going with 12 mm diameter bar as a preferred bar and size. Okay, so your design code, so you need to input your design code here. Okay, so this is ACI 318 code. Then once you're done with that, so we are not designing for any beam, we're not designing for any pre-stress, so we can leave this as it is. Click on OK. Then go back to the design menu, click on concrete slab beam design. Then let's select the design combo. So make sure the design combo, you have your envelope set, like your envelope, as you can see the envelope strength, because we are going to be using this for design. Okay, then click on OK. Okay, so once you're done with that, you can simply go to the design concrete slab beam design. Then you can click on click on start design and check. Let me see. Okay. So you can run analysis. First of all, you have to run the analysis. Click on save. Yes. Okay, now the analysis is complete, so we can go to the design. So design, start design check. Okay, so these are fine. So we can simply click on design, start design check, start design check. Okay, so now this is done. We are done with the design. So now let's display the design parameters, right? So go to the design, right? Sorry, not click on display, then show slab design. Click on show slab design. Okay, so because we are starting with the strip-based method, right? So we are using the strip-based method for now. So let's see the reinforcement in layer A, right, which is in the S direction. So let's first of all turn off the layer B. Layer B is the reinforcement going in the Y direction, but the reinforcement going in the S direction is layer A. Okay, so click on this. Then first of all, let's click on show rebar intensity area, which is this slash unit. So click on apply. Okay, so this is the, as you can see, so we have show top rebar and show bottom rebar. So let's also show the top rebar. Okay, show top rebar and also for bottom rebar. Click on apply. Okay, show top rebar and also show bottom rebar. So make sure this is layer A. Okay, so it's very important. So now as you can see, let's take a look at this particular strip. Okay, so now you can see for layer A, which is, you see, this is showing us the reinforcement demand. This is showing us the reinforcement demand along this strip in the S direction. Right? This is showing us the reinforcement demand along this strip in the S direction. So this is what it means. It is showing us the reinforcement demand along this strip in the S direction. So you can see we have this large. You can see this large yellow area, right? You can just zoom in a bit. You can see this large yellow area. So this large yellow area will represent the bottom reinforcement demand, right? So first of all, let's turn off the top okay, let's leave it as it is. But for this this yellow area, so if you zoom in properly, let's zoom in properly so that we can see this. Okay, yeah, so we can see this properly. Let's zoom in. Okay, something like this. So now you can see this yellow area. This yellow area represents the bottom reinforcement demand, right? Because we know that when a column pushes down on the center of a footing, right? When it pushes down on the center of a footing, the soil pushes back up on the edges, right? On these edges. So these edges, we are going to be having the top reinforcement, right? While at the bottom, we're going to be having the bottom reinforcement. So because the soil pushes back up on the edges, this causes the footing to bend like a bow. It causes the footing to bend like a bow or like a smile, which will create severe tension at the bottom of this footing, right? So at this part, we are going to be having severe tension, like massive tension at this part, because the column is, the column pushes down on the center of the footing, right? So this part, we're going to be having severe tension, right? Which is at the bottom of the concrete. Okay, so you can see, take a look at this demand. So we are taking a look at the show rebar intensity area / unit width. So this is just showing the demand, right? So if you take a look at this value, you can see, if you take a look at this value at this part, we need we're having a demand for the rebar at the bottom part as 540. You can see this is 540 millimeters square per meter. But take a look at the top. Take a look at the top bar. The top bar is showing just 0.11. millimeter square per meter. So it is almost 0. So you can see at this bottom part, we can see the demand is highest at the middle part, right? Because at this part we're having 540 millimeter square per meter, right? But when we go close to the edge of this footing, right? So take a look at this part. Look, what is the demand? The demand is 37.68 millimeter square per meter. So when you compare this to the demand at the bottom, which is 540, you can see that the demand at this bottom is way higher than the demand at the top, right? Because this bottom is experiencing massive tension because the column is trying to push down at the center of the footing, so which is going to create severe tension at this part. Okay, so we can see for this red, you can see this top part where we have the red color. You can see this is almost invisible. You can't really see it, right? Because this part is almost invisible. So this part happened because the edge of the footing can sometimes experience slight reverse curvature, or what we call localized stress. Okay, so for normal standard isolated footing, these top values, you can see, because these top values that is being displayed in red color, these top values, they are usually so small that we can even ignore them, right? So the top steel is typically not provided like for most isolated footing. So you tend to provide top steel for most isolated footing. That is when the footing is really, really massive. So if the footing is massive and it is showing a high top and steel requirement, then you have to provide a top and steel. Okay, but for our standard residential two-story building, you can see this top steel requirement. You can see we're having 37.58. This top steel requirement is so less when compared to the bottom steel. So we can ignore the top steel and just provide the bottom steel, which is so the requirement here is 540 millimeter square per meter. Okay, and this is in the S direction, right? This is in the S direction. So you can also take a look at this in the Y direction. So this is going to be the strip, that is the strip B, which is moving in the Y direction. So for that, you need to click on layer B, turn off layer A, then click on apply. Okay, so you can also get this in the Y direction. Okay, you can see. So this strip is running across the width of the footing. So that is why. So that was the reason why we define the strip width. We define the strip width to run across the width of the footing. So we define the strip width to be half of the width of the footing, so that when you add up, from the left to the midpoint of the footing, from the midpoint to the other side of the footing, it gives you the total width of the footing. Okay. So also take a look at this. You can see the demand for this is also 540. Okay. Then when we get to the top, the demand is so less, like it's so little compared to the bottom. So we can just ignore the top and steel. Okay. So let's move back to the layer A, turn off layer B. Okay. So this is the strip and base method. So you can see how easy we are able to interpret. The reinforcement area. Okay. So this is for the top and also for the bottom. Now, this is where you want to pay close attention. So if you take a look at this reinforcing display type, you can see we are this value is being highlighted, right? Show rebar intensity, that is area per unit width. Okay, so because of this, because we selected this, because of this setting, meaning the number, that is the number in the center of your diagram, right? In the center of this diagram, which this value, which look like a 540, right? This is not your total area of steel. So don't take this as your total area of steel. No, don't take this. Don't make this mistake. What this value indicates is this number is just the density, right? So it is the density of the steel per meter width, right? Per meter of width. So this is so what this is doing is this is only telling you the concentration of steel that is needed right at this specific point. So the concentration of steel that is needed at this specific point is 540 millimeter square per meter. So this is just the density, but this is not telling you the total area of steel. So you need to understand this. So that is why it's very important you understand this. So if you want to get the total area of steel, you need to move from show rebar intensity area / unit width. You need to move to show total rebar area for strip. So you want to click this, then click on apply. And now you can see, so first of all, you need to make sure the impose minimum reinforcing option is always checked. It's very, very important, because if it is unchecked, then SAFE is only going to show you the raw mathematical steel required for the load. Okay, but however, the ACI code state that we must always have a baseline minimum steel of like 540 millimeters square per meter to prevent temperature and shrinkage and crack. Okay, so you can take a look at this on the code. So you can see, so this is the reinforcement limit. So the minimum area, so in section 7.6, right? In section 7.6, the ACI is saying the minimum area of flexible reinforcement AS/M of, so it is 0.0018 AG. So AG is the gross area, right? So AG is the gross area. So because this is per width, so this AG is going to be per meter width, which is going to be 0.0018 multiplied by 1000 millimeter. Then you have to also multiply this by the thickness of your footing, right? So it's going to be 0.0018, right? Then multiply by 1000 millimeter, right? Then you have to multiply this by the thickness of your footing. So we know the thickness of this footing is 300 millimeter, right? So you have to multiply this by 300. So which is going to give us the minimum. Is going to give us the minimum reinforcing as 540 millimeter square per meter. Okay, so that is why if you turn off this and click apply, you can see we're having 178, and you cannot use this, right? You cannot use this. So the code is not, the code is not using the minimum reinforcing. So this value is way below the minimum reinforcing. So that is why you always want to click on impose minimum reinforcing, then click on apply. Okay, you click on apply. So now as you can see, ACI the code is going to give you the minimum reinforcing, but this is for the total rebar area. But if you move to show rebar intensity, so this is where this will apply. Click on apply. So now you can see the code is giving you the rebar intensity, right? So, and it is forcing you to use the minimum, which is 540 millimeters square per meter. So that is why it is very, really important you turn on this. It is important you turn on this impose minimum reinforcing. So I hope you understand this. So if you let's go to the show total rebar area for a strip. So this is highly recommended for isolated footing. So this is what you want to select. This is what you want to use for isolated footing, because what this does is it take the intensity, this show rebar intensity, it take this and multiply it by your exact strip width automatically. Okay, so the output of this is going to give you the total millimeter square for that specific footing lane. Okay, which is going to let you to calculate your rebar instantly. So it's going to let you to calculate your rebar, which is the bar size you'll be needing, right? Which is the bar size you'll be needing for your footing. But if you select this show number of bars, right? Show number of bars of size. So what this does is, this is a shortcut tool. So if you select this, you can type your intended bar size. So let's say if you want to use bar size 12, bar size 10 millimeter, 14 millimeter, 16 millimeter, you can input this into this bus, right? Then what SAFE will do, SAFE is going to change the diagram number, right, from square millimeter to an actual count of bars, right? So SAFE is going to tell you, okay, since you are using 12 millimeter bar, then meaning this is the number of 12 millimeter bar you are going to be using across the span of the footing. Okay, so this is what it does. Okay, so this is for the bottom bar and also for the top bar. But if you are providing top bar, then you also input the diameter of the bar you are going to be using for the top bar. But because we are not using top bar here, because of the area of steel required here is so little, so we can just ignore that, right? So we are only going with the bottom bar. Okay, then for this particular value where we have show rebar above a specified value, so this shows this. If you click on none, this is going to show you the total steel required from 0, right? It's going to show you the total steel required. But if you select this typical uniform reinforcing specified below, so if you select this, the empty input bus below, it will unlock, right? This is going to unlock, and you can test SAFE. So let's say, for example, I'm already placing a default grid of, let's say, 12 millimeter bar, and these bars are spaced at, let's say, 200 millimeter spacing across the entire width of the footing. So what SAFE will do is SAFE will subtract that baseline mesh capacity from the demand. So if you want to check if this is enough, right? So you can input your bar size at the bottom and also the spacing, okay, and the spacing. So what this is going to do is the diagram will then show you zero, like 0 over footings, like where that baseline mesh is strong enough. Okay, so it will display a color spike only if a heavy column will require additional bars, that is top stairs on the top of your baseline grid. Okay, so it is going to show you, okay, do you need an additional bar or not? So you are going to know if you need additional bar. That is, if you provide this, let's say if you provide 12 diameter bar and you provide the spacing, so it is going to show you if this is enough or not. If it is not enough, it is going to show you where you need to, the additional bars you need to provide. Okay, so that is for this typical uniform reinforcing specified below. Okay, then if you click on this reinforcing specified in slab rebar object, so this function exactly like like this option, like this typical uniform reinforcing specified and below. But instead of typing a specific value, right? Instead of typing a specific value like the bar size, the spacing. So what this does is it reads the actual physical rebar component you have molded directly inside the software. Okay, so we tend to go with this. I'll go with this and none, so that it will give me the required total steel area, right? So this is what I'll be selecting this. Okay, so now for layer A, which is in across the S direction for layer A, so what I'm going to do for layer A, okay, so since we are not using top rebar, so there's no need for us to show top rebar. So I can just deactivate this top rebar. Then what I need is so I can click on this show total rebar area for strip, right? For this strip, then click on apply. So now you can see if you click on this, then just need to zoom in to see. So this is the required area of steel that is needed. So if you can see the required area of steel that is needed for this, right? For this is 648 millimeters square, right? So you need to provide 648 millimeters square of rebar that is running across this S direction, right? That is running like this, running in the S direction, right? This is what you need to provide. So you have to now find let's say the bar diameter, right? The bar diameter that will be enough for this 648. Okay, so this is how you can detail your reinforcement using this strip method along the S direction. Okay, but what I will do, I will use this third option. I'll go with this third option, click on show number of bars and size. So now let's say, since I know that I want to use 12 diameter bar, or let's say, for example, let's say I go with 18 diameter bar, for example. If I go with 18 diameter bar, that is for the bottom, right? I'm not taking a look at the top. I'm only taking a look at the bottom. So I'm going to see how many bars of 18 diameter bar do I need, right? How many number of 18 diameter bar do I need? So click on apply. Now if you see, take a look at this. So you can see, so CSI SAFE is saying we need 3 18 diameter bar, right? We need 3 18 diameter bar. But now this is where you need to pay close attention. So if you need 3 if you need 3 18 diameter bar, that will be placed along along the S direction. Now what will be the spacing? And according to ACI code, the maximum spacing, you need to make sure that this spacing, it does not exceed like 400 or 450 millimeter, because according to ACI code, the maximum spacing for a rebar, like let's go to the code. So this is the minimum area of steel, right? We know this. So the maximum spacing, so you need to make sure it doesn't exceed the maximum spacing. So the maximum spacing for this, let's see, Flexura, right? For Flexura, what is the maximum spacing? Non-pre-stress shrinkage. Okay, I think we missed it. So just move up in the list. This is combination of Flexura for pre-stress slab. Combination of reinforcements. Okay, this is flexural reinforcement in, okay. Yeah, so we can see here, this is the maximum spacing S of reinforcement required. So this is for, you can see, required by 7.5.2.3 shall be the lesser of 5H and 450 millimeters. So H is basically the thickness of your footing. So we know our footing is 300, right? 300 millimeters. So 300 multiplied by this 5 is going to give us 1,500 millimeters. So, and the lesser of this is going to be your lesser spacing. It's going to be your maximum spacing, which is 450 millimeters. But as per our side practice, most we tend to go with 300 millimeters as a maximum, because we don't want we don't want this the spacing to be too high, and which can affect the strength of our footing. So we tend to go with 300, but as per ACI, you can see this is 450 millimeter. We can say 300 millimeter as a maximum. So we don't want to exceed that, right? So and the minimum is somewhere around 25 millimeter. Okay. So now let's see. Let's go back to CSI SAFE. So now we know we are needing just three 18 mm diameter bar. So let's see what if we place 3 18 mm diameter bar across, going in this direction, what will be the spacing, right? What will be the spacing? So basically, for that, what will be the spacing? So I'm just going to calculate this so that let's go to, okay. So what I'll do, I'll just move down list, okay. So for this, what will be the spacing? So now what we need to do is we need to know the total width, right? The total width, okay. So total width of this footing. So we know this footing is 1,200 millimeter by 1,200 millimeter, right? So total width is 1,200 millimeter. Okay. So this is the 1,200 millimeter. Then also we need the cover. What is the cover? So the cover, right? So the cover is going to be on both sides, right? Cover at both sides, right? Because we know if we are placing rebar like this, if we are placing rebar along, going in this S direction, there will be cover on this side, right? On this side also there will be cover on this side. So we know the cover is 75 millimeter, right? So because it is two sides, it's going to be 75 millimeter multiplied by 2, right? So I hope you understand this. So cover at both sides is going to be equal to 75 millimeter. Then you have to multiply this by 2. Okay, so 75 millimeter multiplied by 2, this is going to give us 150 millimeter. Okay, so this is going to give us 150 millimeter at both sides. Okay, so now the effective dimension. So this effective, so I'm going to have the effective dimension. Okay, so just pay close attention to this. So the effective dimension is now going to be equal to this total width minus the cover at both sides, which is going to give us 1,200 millimeter, then minus 150 millimeter, right? So when you calculate this, you are going to get 1,050 millimeter, right? 1,050 millimeter. Okay, you're going to get 1,050 millimeter. So now we know the effective dimension. So now we need to know the number of spaces, right? So the number of spaces is going to be equal to the number of spaces. So we know we're having 3 bars, right? So it's going to be 3 bars. Then we have to subtract 1, right? We have to subtract 1. So 3 bars minus 1, we're going to get 2 spaces, right? So if we're having 3 bars, then meaning the spaces is 2 spaces, right? Okay. So 3 bars minus 1 is going to be equal to 2 spaces. Okay. So 2 spaces. So now the final spacing is now going to be equal to the effective dimension. So the effective dimension, which is this 1,050, right? Then you have to divide this by the number of spaces, which is 2. Okay, so 1,050 divided by 2. Okay, so you just have to calculate this. So 1,050 divided by 2. So now as you can see, we're having a spacing of 5. So we're having a spacing of 1,000 divided by 2. So we're having a spacing of 525 millimeter, and this value is way greater than the maximum, which is 450, or we can say 300 millimeter. Okay, well, as per side practice, we tend to go with 300 millimeter. So this is greater than this, which is not okay. So as you can see, this is not okay. We cannot provide 18 diameter of provide 18 diameter bar because the spacing is going to be extremely too large, right? So we can't do this. Okay, so I hope you are understanding the logic. So in that case, what we can do, so we need to, since this is just a 2-story residential building, and so we don't really need a high bar diameter, right? So we can just reduce the bar diameter. If you reduce the bar diameter, this will automatically reduce the spacing, right? So let's say we go with a bar diameter of 12, right? So if you go with a bar diameter of 12, then click on apply. So now as you can see, if you go with a bar diameter of 12, we are needing 6 12 diameter bar. So now let's check the spacing for 6 12 diameter bar. So if you check the spacing for 6 12 diameter bar, so the total width remain the same, cover on both sides remain the same, the effective dimension remain the same. Now the number of spaces is now going to be 6 bar, right, minus 1, which is going to give us 5 spaces. So now we have 5 spaces, right? So spacing now is going to be the effective dimension, which is 1050, then divide by 5. So 1050 now, 1050 divided by 5. So we are going to get the spacing to be 210 millimeter. So 210 millimeter, this is lesser than 300 millimeter. So we are good to go. So this is okay. So this is fine. Now you can see. So this is how you can, this is how you can detail your reinforcements. Okay. So you just need to understand the logic behind this. So now we can categorically say that for in the S direction, the rebar that is running in this direction, we are going to use 12 diameter bar, 6 in number, and the spacing is going to be 210 millimeter. Okay, the space is going to be 210 millimeter in the S direction. Okay, so you can also provide the same in the Y direction, like which is for layer B. Turn off this layer A, click on layer B, then click on apply. So since we're having the same value, right? We're having the same, we can see 6 12 diameter bars. So we're having the same value. So meaning you are going to say your final reinforcement design is going to be, you are using 12 diameter bar, 6 in number at a spacing of 210 millimeter at both sides, in the S direction and also in the Y direction. So you can see this is how we can quickly detail our rebar in the footing. So you can see, I hope this is understood. So let's quickly also take a look at the rebar for this other footing. For this other footing, we defined a different strip. We drew a different strip size on this other footing because the size of this footing is different compared to this other footing. Okay, so as you can see, if you take a look at this, so we already understand the concept now. So for this layer A, let's click on apply. So yeah, for layer A, now you can see what do we need. I'm taking a look at just the bottom rebar. So now you can see we are needing a 8 number. We are needing a 8 12 diameter bar, right? So we are going to be using 12 diameter bar. We are using 12 diameter bar, and this bar we are going to be having 8 of these 12 diameter bar that will be spaced along in the S direction. While in the Y direction, I think we're also going to be having the same. In the Y direction, yeah, in the Y direction we're having the same, right? Because this is a square footing. We're having the same in the Y direction. Take a look at the top rebar. For the top rebar, you can see for the top rebar, you see that is why we don't need the top rebar. Like I said earlier, we don't need the top rebar. So for the top rebar, you can see we're having a 2 6 diameter bar, and no one is going to be using 6 diameter bar, for footing, and we're having just 2. So that is why this is so little. So we can just ignore that. Okay. So for now, you can see. So for this particular bar, for this particular foundation, for this particular footing, so since we are going with 8 12 diameter bar, so you can just calculate the spacing for this. So if you want to calculate the spacing, so since the number of spaces is going to be, how many bars we have? I think we're having 8 bars, right? So it's just going to be 8 bars, like minus 1. So meaning we are getting 7 spaces, right? So since it's 7 spaces, now you have to divide this by 7. Okay, so it is going to be 1050, then divide by 7. So we're getting a spacing of 150 millimeter, which is also fine. As you can see, this is lesser than 150 millimeter, which is lesser than 300, and also it is greater than 25, because 25 millimeter is the minimum. You cannot go below that. So okay, so this is 150 millimeter, which is lesser than 300 millimeter. This is fine. Okay, so we can also provide this type of rebar. And I think we also have a different type of a footing with a width of I think the width was 1.6 meter, right? Yeah, for this footing, yeah, the width is 1.6 meter, you can see. So let's take a look at layer A, turn off this layer B. So let's see, click on apply for layer A, right? So for this footing and this footing, they are different. So for layer A, let's see what are we having. Okay. So for layer A, you can see, so you can see if we provide a 12 diameter bar, we are going to be having 15 of 12 diameter bar spacing in the S direction, right? We are going to be having 15, and I think this might, the spacing might be too, the spacing might be too little, right? But let's just check. Let's check for this. What do we have? Okay, for this we are also providing 12, but the spacing is the number of bar we are having here is 19. Okay, so let's see. Let's take a look at this. Let's see. So if we're having 19 bars minus 1, so the spaces is going to be 18. We're going to be having 18 spaces, right? 18 spaces. Now this divide by 18. Okay, so this divided by 18, we're going to get 58. So the spacing is just 58, although it is lesser than 300 millimeter, but it is going to be really, really difficult, to compare the concrete, because this spacing is quite, although the minimum is 25, but for workability purpose on site, you can't really go with 58 diameter spacing. It really doesn't make any sense, because it is going to make, it's going to be very difficult to compare the concrete and all that. So that is why we cannot go with this. So in that case, what we can do for this, for this particular footing, let's say we can increase the bar diameter. If you increase the bar diameter, this will automatically increase the spacing, right? So let's say we are going with 16 diameter bar for this. Click on apply. So if you go with 16 diameter bar, now you can see the spacing has reduced. For this particular bar, we're having a spacing of we're having the number of bars as 11. Okay, number of bars 11 for this. So we can say right. Okay, effective dimension, yeah, spacing, total width, covered both sides is 75, effective dimension. Okay, so for this, since we're having 11 bars, right? We're having 11 bars, so we can quickly calculate this. So instead of 19 bars, we're having 11 bars. 11 minus 1 is going to give us 10 spaces, right? So this divide by 10, so the spacing is obviously going to increase now. So this divide by 10. So now we're now having a spacing of 105 millimeter, and so we can go with this spacing 105 millimeter, something like this. So, or we can just run this, since the spacing is 105, yeah, we can go with this spacing 105 millimeter. So we can do something like this. So this will be perfect, right? This will be better compared to the previous one. Okay. So therefore, this we're having 16 diameter bar, 9 in number, right? 9 in numbers. Right, so for this, we can also calculate this. So since we're having 9 numbers, so it's going to be 9 bars, then minus 1 is going to give us 8 spaces, right? 8 spaces. So now you have to divide this by 8. Okay, we have to divide this by 8. So if we divide by 8, if you divide this by 8, we're going to get the spacing as 131.25. Okay, 131.25. So this 131.25 is okay, right? It is fine, but we can just round this up to like let's say 135, or let's say 130, right? You can just round this up to 130, but it is better we use yeah. So now no problem, we can just round this up to like 130 or 135 as well. Okay, so this is fine. We can go with something like this on site. So this is how you place your bars. Also in the y direction, which is layer B. So I think we're also going to be having the same value, right? So it is same. You can see we're having the same value for this. So this part is 9. Then this is 10, right? So this part is 10. Like layer B for this part is 10. While layer A, for layer A we're having 11 here, and for layer B we're having 10. Okay, so you can just place your rebar as per the spacing and also the number of bars. So you can see this is how we can. So you see how easy it is to to use the street-based method to design your footing and to get the reinforcement. So now you understand the difference between this, and also you understand the difference between this, and this. Okay, so in most cases we are going to be using this non-option and this show number of bars or of size, show number of bars of size. But if you want to just get the area, click on this, get the area, then you can manually calculate the diameter of the bar that is needed to satisfy the area and also the spacing. Then you can go with that. Okay, you can go with this value. Okay, so this is how we can use the strip-based method to design our isolated footing. Now we understand the strip-based method for designing the footing. Now let's take a look at the second design method, which is the finite element-based method. Okay, so you want to click on the finite element-based method. As you can see, for the finite element-based method, so what this does, so this finite element-based method is going to tell CSI SAFE to stop looking at the rigid strip lane we drew earlier, right? And instead, it is going to tell CSI SAFE to look at the tiny mathematical mesh, like that, the tiny mathematical square mesh, which is the finite element that make up the concrete part. So what this does is, so instead of your reinforcements to be displayed, instead of your reinforcements to be displayed on this rigid strip lane, which you drew on the footing, your reinforcement is going to be displayed. Your reinforcement is going to be displayed using a heat map. Okay, so with this heat map, you can find your reinforcement. You can find your area of ST. Okay, so this is what we call the finite element-based method. Okay, so you also want to click the impose minimum reinforcing. So this is very important, so that you this is going to ensure that your heat map, right, it will never drop below the ACI code minimum for your footing thickness. Okay, so it will never drop below the 540 millimeter square per meter. Okay, so that is why we also want to click the impose minimum reinforcing. Now for the reinforcing direction and location, so direction 1, so we're having two directions. Direction one, this is basically the S direction, right? Direction 1 is the S direction going in this direction, while direction 2 is the Y direction. So we're having direction 1 top bar, right? Direction 1 bottom bar, direction 2 top bar, and direction 2 bottom bar. So because we said this is we are designing for isolated footing, so in most isolated footings, you don't even need the top bar. You don't need the top reinforcement, because these values are so little that we don't even need to provide top rebar. But if your footing is very massive and you're having a high rebar demand at the top, then obviously you want to provide a top rebar in direction 1 and also top rebar in direction 2. So, but we mostly provide a top rebar for combined footing, or we can say mat footing. Okay, but for this case, let's just focus on the bottom rebar, because this is where we are going to be having the high shear. We are going to be having high stresses on the bottom, right? And we're going to be having high tension at the bottom, because the footing is trying to the footing is trying to punch the column is trying to punch the footing down. So at that region, it is creating high tension. So that is why we are going to be looking at the bottom rebar direction 1 in the S direction, and also the bottom rebar direction 2, right? The bottom rebar direction 2 in the Y direction. Okay, so I hope you understand this. So let's take a look at the bottom rebar. Then make sure you click on impose minimum reinforcing, then click on apply. Now as you can see, so we the reinforcement is we no longer have our strip, right? So you can see we're having instead of strip, we're having heat map. You can see, so these are heat map, right? You can see these are heat map, and these values are in millimeter square per meter. So as you can see, for the contour averaging at node, we are selecting by object, because finite element math can sometimes produce unrealistic resulting spike of infinite stress right at the exact center point of the column. Okay, so by averaging by an object, that is by selecting by this object, so this is going to smooth out those spike out, or this is going to smooth out those spike out. This is going to smooth out those spike out, right, over the width of the column, and it's going to give you a more realistic and also a more constructible steel demand. Okay, so that is why we are going to be going with by object. Okay, so now let's see how can we rate this reinforcement. Now take a look at this. Can you notice how almost all of the footing on the perimeter, like all the footing on the perimeter, they are showing a solid red flat color, right? You can see almost all the footing at the perimeter are showing almost solid red flat color, right? You can see. Okay, so if you match this red, if you match the red to the color bar at the bottom, you can see this is the color bar at the bottom. So what this does is it corresponds to the lowest value on the scale, right? So this is the lowest value on the scale, the heat map, we started from purple, then it moved to a red, then it increased all the way to blue. Okay, so these values are the lowest values on the scale. So why is this so? Because we check the minimum imposing, as you can see, we check the minimum imposing reinforcing. So these solid red lines, this means that the footing only needs the basic code minimum steel. So meaning at this perimeter footing, there are no high stress concentration. So because there are no high stress concentration, CSI SAFE is giving us the minimum steel requirements for this perimeter beam. So that is why you can see that the heat map showing the heat map color showing on this perimeter footing. So this color are they are at this color, they are the lowest value on the scale. You can see, so starting from purple to red. Okay, then now take a look at if you take a look at this middle part of the footing. So look closely at these two footing. You can see there, look closely at these two footing. You can see that they have a red perimeter, right? They have red perimeter heat map. But when you get to the center, you can see the center bursts into yellow. You can see bursts into yellow, and also from yellow it turned to green right under the column. Okay, so what this indicates, so what does this indicate? This indicates that these columns, like these two columns, they are carrying heavier load when compared to the other footing. Okay, so these two footing, they are carrying like heavier load when compared to this other footing. Okay, because you can see this the heat map for this particular footing. So we're having a heat map of a green color heat map, and which is which, if you take a look at this color range, so this is the heat map. Okay, so which is greater than this than the red color heat map. Okay, so this green color, this green peak is going to indicate is going to indicate a localized area where the bending stress is so high, right? It's so high that the code minimum steel is no longer enough to stop the concrete from cracking. Okay, so I hope you're understanding this. So let's try to understand these values, right? So if you over your mass, exactly over the center of this green hotspot, you can see over the center of this green hotspot. So you can see a value of, like, let's say 2147.05 millimeter square per meter. You can see that. You can see this number. So here's the tricky part about finite element method for isolated footing. So you cannot just take this value. You can't just take this 214705 millimeter square per meter, this peak value, right? You can't just take this and divide it by your bar size. And divide it by your bar size, as in to get your number of a bar or the spacing. You can't do this, because if you do this, then you grossly over design your footing, right? You would grossly over design your footing. This value 2147.05 or any other value 151, these values. So these values, what this value does is, like, they only exist right at any tiny 100 millimeter, center point under the column. Okay, so the edge of the edges of the footing, that is this red part, need much less, right? So this part need much less, but here we need more, more steel. So if you are designing a standard isolated footing, normally the strip-based method is vastly superior and much faster for getting your final bar count. But however, if you must use this finite element method, engineers, they handle this hotspot using what we call the typical uniform reinforcing specified below, which is this. So instead of using this known value, you can see, instead of using this show rebar above specified value, because you can't just take these values. You see these values. You can't just take these values and you can't just take these values and divide it by your bar size. you are going to, you are going to over design. You are going to over design your footing, and which will not be realistic. Okay, so what engineers do is, instead of going with this non-value, they normally go with this typical uniform reinforcing specified below. That is for the finite element base. Okay, so what this does now, so what you're going to do with this value now, so you're not going to input your bar, your bar size, like the bar size you intend to use for this footing, and also you're going to input the spacing, but this spacing should not be more than the maximum spacing. Then after inputting the spacing, then you check. Okay, then you check if there is additional rebar, like if this bar diameter and the spacing is sufficient enough to withstand the stress that is coming on this footing. Okay, so if it is sufficient enough, then there will no longer be any heat map on your footing. So the heat map on your footing is going to turn completely gray. So that is going to indicate that the bar size you specified and also the spacing is enough. Okay, but if you see maybe extra heat map, so meaning you will need like extra, you will need like extra steel in that zone. Okay, so let's see this. Let's see how this work. Okay, let's see how this works. So let's say we want to provide 12 mm diameter bar, and the spacing, let's say we want to go with the spacing of 200 millimeter. Okay, so now we are trying to check this. We want to go with the spacing of 200 millimeter, and this is in the S direction, right? So bottom rebar in the S direction. Now let's click on apply. Now if you click on apply, you can see at this part, you can see we're having zero requirements. You see, we're having zero requirements, zero. So meaning this for this footing, it is sufficient, right? So we can provide 12 mm diameter bar at 200 millimeter center to center spacing. It is sufficient because you can see there is no extra rebar required. You can see, take a look at this value. They are showing zero requirement, zero. So no additional rebar is required. So meaning this can satisfy the reinforcement in the S direction for this footing. But if you take a look at these two footing, like they won't be sufficient enough, right? So we need to provide extra rebar. Okay, so this is how you detail your reinforcement. So for this, for this footing, apart from these two footing, we can provide 12 mm diameter bar, 200 millimeter center to center spacing. Okay, let's say if we increase the spacing by 400. Okay, now if you increase the spacing by 400, you can see it will not be sufficient. You can see, so there are extra rebar required. You can see the extra rebar required. So we can provide 200 millimeter spacing. Okay, so if we go with 200 millimeter spacing, let's try 300 millimeter spacing. You see 200 millimeter spacing is still not sufficient. There are still additional rebar required. You can see there's still additional rebar required. So we can just go with, let's say we go with 250 millimeter at the bottom. So 250 millimeter is sufficient. You can see 250 millimeter is sufficient. So we can go with 250 millimeter, or we can go with 200 millimeter. So if you go with 250 millimeter, so if the more spacing we have, more spacing is going to lead to less rebar, right? So less rebar is going to lead to a more economical design. So let's say we go with 250 millimeter. Now these are for the columns. Sorry, these are for this footing. Okay, then you can also provide the same in the Y direction. So the Y direction is going to be direction 2, right? So let's see if it is also going to satisfy the Y direction. So you need to click on direction 2 bottom rebar, then click on apply. So as you can see, it is also satisfying the Y direction. You can see, so it's also satisfying the Y direction. Okay, so the final design is going to be, we are using 12 mm diameter bar at a spacing of 250 millimeter center to center spacing. Now we need to provide extra bar for this other two, for this other two footing. So let's say, so in this case, let's say we are providing 16 mm diameter bar, right, with a spacing of 200 millimeter for this. Okay, click on apply. So you can see there are still additional reinforcement. There are still additional rebar required for this. There are still additional rebar. So let's say we provide a 150 millimeter spacing. So 150 millimeter spacing is going to lead to less T. So less T is going to satisfy this requirement. So let's see. Okay, so we still need more. So let's just go with 100 millimeter. Let's see, 100 millimeter. Click on apply. So 100 millimeter, we still need more for this. We still need more for this. So let's say we go with Okay, let's say we'll go with 75 millimeter. Click on apply. So for 75 millimeter, you can see 75 millimeter, we don't need any additional steel. So the final design is going to be 12 diameter bar at 250 millimeter center to center spacing for this footing. And for this footing, we are going to be using 16 diameter bar at probably 75 millimeter center to center spacing or 100 millimeter center to center spacing. Now that we understand the finite element-based method and the history-based method for designing the isolated footing, now let's see if we can also provide mat foundation for this footing. Okay, so we know that if you want, when you're providing mat foundation for your footing, meaning your soil is very weak, right? The safe bearing capacity of your soil is weak, right? And in order for the soil to be able to properly transfer the load, as into more area, then you have to provide a mat or raft foundation. Okay, but there are also other reasons why we tend to also provide mat foundation. So one of the reasons is let's say if the total area of your individual footing, that is of your individual isolated footing, if this total area cover more than 50% of the building total area, then why not just provide mat foundation? Because the total area for the individual footing is more than 50% of the total. Is more than 50% of the site and plan. Then providing isolated footing is just going to be a waste of money, and it is going to be very difficult to excavate the footing on site. So in that case, why not just provide mat foundation? Okay, so this is a general rule. Most structural engineers they go with this rule. So if the total area of your individual footing is less than 50% of your total building area, then it is fine. You can go with isolated footing. Because it is not going to cause problem with excavation. But if the total area of each individual footing is more than 50%, let's say it is 60 or 70% and above, then you need to stop providing isolated footing, because going with isolated footing is going to be a waste of time, it's going to be a waste of resources, and it's going to be very difficult to construct on site. So in that case, you just provide one large area for your footing, and this is what we call the raft foundation. Okay, so I hope you are understanding this. So now you might ask the question, like, why are we placing a 50% threshold? Like, why? So I already explained this because first of all, because of the overlapping excavation, right? Because you know that if you want to dig, let's say you have let's say 20 different isolated footing, and if you want to dig this each of these isolated footing, let's say the thickness is 1.5 meter deep, you need to manually bring excavator, right, to dig at each footing. Now, if this footing, like they are close to it, they are so close to each other, and you try to dig out the soil, right? You try to dig out the soil from the ground. So obviously, you need enough space to be able to place the soil, because after digging out the soil, after placing your reinforcement, then you also need to refill the soil, right? But if this total area of the isolated footing is not more than 50%, meaning there is not enough space. So where will you place the soil where will you place the dirt that was dug from the soil? Like, there will be no enough space, because as you try to dig out the dirt from this soil, also you're also trying to dig out the dirt from this soil. Now, if there is not enough space, then where will you place the soil? Like, it is going to be very, very difficult, like for the excavator to dig out the soil. And also, one of the main reasons why we also place this 50% threshold is because of the formwork and the labor costs. Okay, so imagine you're having, like, let's say 20 or 30 different isolated footing. Like, now you need to manually bring out or cast timber, like formwork for each isolated footing. Okay, for each isolated footing, and this is going to be really stressful for the workmen, right? It's going to be stressful, and also casting out different different formwork for each for different isolated footing. It's also going to cost us more money, right? It's going to cost more, because you need more labor costs, like you need more people like to place this formwork, right? So, but it is significantly cheaper and faster to just build one long formwork, like one long formwork boundary around the outer perimeter of the building, right? So if you're having a mat foundation, all you need to do is just need to build out just one long formwork, in the y direction, and also one long formwork in the x direction. Then you repeat the same in this direction and also in this direction. Okay, so it's going to take less time, and also it's going to cost you less money, right? So that is also one of the reasons why we provide this 50% threshold rule. And also one of the main reason as well is because of the overlapping soil stresses. Okay, because you know that when you push down on isolated footing, let's say you push down on this isolated footing, the stress is going to spread that into the soil in a shape, what we call pressure bulb. Okay, we are going to have a pressure bulb for this isolated footing. Now, if these two large isolated footing, they are spaced very closely together, then the pressure bulb of this footing and the pressure bulb of this other footing, they are going to overlap, right? They are going to be overlapping deep underground. Okay, so this is going to double the stress on the deep soil layer. Okay, which can cause severe and unpredictable settlement issues. Okay, so if the pressure bulb of this footing is overlapping with the pressure bulb of this other footing, then it can cause it can cause severe settlement issues. I don't want such a scenario to occur. So in that case, why not just provide a mat foundation? If you provide a mat foundation, this will completely eliminate this localized overlap. Okay, so that is the reason why we place this 50% threshold. So now let's see if we actually need a mat foundation. So we are going to be calculating the total area of each individual footing, right? Then we are going to now compare this with the total area of the building plan. And if this is more than 50%, then we have to stop isolated footing. We have to go with the mat footing. Now, if it's less than 50%, then we are good to go. We can continue with our isolated footing. So I hope you understand this. So now let's calculate this. So we know that we know the length and width of this footing. This is 1.2 meter by 1.2 meter, right? While for this is 1.5 meter by 1.5 meter. Then for these two footing, this is 1.6 meter by 1.6 meter. So I think we already saw this, right? So I'll just unlock the model, just to confirm. So click on draw dimension line. So from this point to this point, you can see this is 1.2 meter, right? So this value is 1.2 meter. Then so this is 1.2 meters. So draw dimension line. Then this, I think this was 1.5. Yeah, this is 1.5 meter, right? This is 1.5 meter. Then this is 1.6 meter. So you can see, okay. So these two footings, they are 1.6 meter. Okay. So now let's calculate the area of each individual footing, and we are going to add it up. Okay. So now let's say, so we can say the first value, right? The first is 1.2 by 1.2 meter, right? So 1.2 by 1.2, 1.2 by 1.2. So 1.2 by 1.2 this is going to give us 1.44 meters square. Okay. So how many of these do we have? We have how many of these do we have? So we're having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're having 10 of these, right? So you have to multiply this by 10. So this multiply by 10 is going to give us, okay, sorry, just let me put it here, pull it down. So this value 1.44, then multiply by 10. It's going to give us 14.4 millimeters square. Sorry, not millimeter, meter square. Okay, so this is for the first footing. Now the second footing, so I think the size was 1.5 by 1.5 meter. So 1.5 by 1.5, this is going to give us 2.25 meters square. Right, so how many of these do we have? So we have 2.25, then multiply by, so how many of these do we have? Let's see. So this value, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these two footings that are different, So we're having 16 of this. Okay, so this multiplied by 16 is going to give us 36 meters square. Then finally, for the last footing type, this is 1.6, right? 1.6 by 1.6 meter. So this is going to give us 2.56 meters square. Okay, so for this, it's going to be 2.56. They have to multiply this by the number. So we're having 2, right? You can see we're having 2, 1, 2. So you have to multiply this by 2, which is going to give us 5.12 meters square. Okay, so now as you can see, we have successfully calculated the area for the individual isolated footing. So now we need to add this up. Okay, so we need to add this up. So the total area. So we're going to say the total area for isolated footing. Right, so we're going to add this up. So it's going to be this value, right? 14.4, then plus 36 square meter, right? 36 square meter, then plus this value 5.12, okay, meter square. So now we need to add this up. Okay, so we're going to be having a 14.4 plus 36, then plus 5.12. So we're having a value of 55.52, right? 55.52 square meter square. So this is the total area, right? This is the total area for the isolated footing. Now we need to compare this value. We need to compare this value to the total area of the building plan. And this value should not be greater than 50% of the total area of the building plan. If it is greater than 50% of the total area of the building plan, then we provide raft foundation. But if it is lesser than that, then no problem. We can continue with our isolated footing, meaning there is enough space for excavation and and all that. Okay. So now let's go to CSI SAFE. Okay. So you can see we need to find the total area, right? The total area for this. So we can just so for that we can just draw a dimension line. Like we can draw a dimension line that is from this point to this point, right? So let's go to draw dimension line. So we can just draw a dimension line that is from this point to this point. So what is this? This is 70.9. What is this? 70.98, right? So we can say. So now we can say the total area. Okay, so total building. We can say total footing area. Let's say total footing. No, let's say total plan area. So it's gonna be 17. What is this? 17.98. Right, so 17.98, then multiply by. So then from this point, right? So this is the other. So this is what? This is 17.072, right? 17.072. Okay, 17.072. So multiply by 17.072. So this is going to be equal to. So now as you can see, the total plan area is 300 and let's say 306.9 millimeter. Sorry, not millimeter, meter square. So the total area is 306 meters square. Why for this, the total area for the isolated footing is 55.52 meters square. So now, so me looking at this, I think it's already passed, but we can check this value, right? So E, let's just call this value E, for example. So it is going to be equal to this value, right? The total area of isolated footing, which is 55.52, right? Then let's divide this by this value, right? Which is 306.9. Okay, so we can put this in parentheses. Then I will have to multiply by 100 so that we can get this in percentage. Then multiply this by 100. Okay, so what is this value? So as you can see, we are getting 18.8. So we are getting 18%. Right, we are getting 18%. So 18% is obviously lesser than 50%. right? So because 18% is less than 50%, then we can say therefore, therefore continue using isolated foundation. All right, so we can say continue using isolated foundation. Okay, so this is the check. So now you can see, so this is how you can quickly decide if you are going with isolated footing or you are going with combined footing. But because this is less than 50%, then no problem, we can continue using isolated foundation.